Okay, so hello everyone. Welcome to the sixth edition of our Quantum Machine Learning Conference. It's an online conference organized by Q Poland and Fundacja Quantum AI. So Fundacja Quantum AI is a non-profit organization that I founded a few years ago to support education and research and collaboration in new technologies, especially quantum computing and AI, and also intersection of quantum computing and AI. And Q Poland is a quantum community in Poland supported by Fundacja Quantum AI, and it's one of the Q cousins of QWORD. So QWORD is an international organization contributing to the development of the open global ecosystem for quantum technologies and democratizing access to the quantum education. So as you can see, I will start by giving the introduction to quantum machine learning, but actually this is the plan for today. So there will be my introduction. Later, Sven Groppe will give a talk about data quality in the area of quantum computing. So I saw that Sven has joined as well, which is great. And then Arthur will give a talk about adaptive measurement allocation for learning kernelized SVMs under noisy observations. And later, Jacob Cybulski, who is with us as well, will tell us about paradoxes of high-dimensional quantum models. And then Sebastian Jura, who is now joining, will give a talk about multi-source classification with quantum architecture search. And finally, Karol Bartkiewicz, who has just joined as well, will give a talk about quantum associative memory with photonic quantum memory stores. So the agenda looks very good. So every talk will last about 25 minutes, and there should be a few minutes for the Q&A. So if you have any questions during the talks, you can post your questions on the chat, and um, we'll try to answer the questions at the end. If there is something urgent, you can also try to raise your hand, and if the speaker has a time, the speaker can try to reply. But I recommend keeping all the questions for the Q&A at the end. All right, so let's start the introduction to quantum machine learning. So actually, it's good to know that when we talk about quantum computing and machine learning, there can be uh, two intersections actually, right? So of course, we can think about applying classical machine learning algorithms to solve some classical problems, and this is just a classical machine learning that we know: classical neural networks, decision trees, SVMs, large language models, and so on. So we know it. But we can also think about enhancing classical machine learning with quantum methods. So this is what people often call quantum machine learning, or actually quantum enhanced machine learning, because there can be also another intersection of machine learning and quantum technologies, the application of classical machine learning to develop better quantum technologies or to enhance quantum technologies. So in this conference, we'll primarily focus on this quantum enhanced machine learning part. So how to enhance, how to improve or how to solve classical or maybe sometimes quantum problems using quantum computing. So actually, this fourth box here, so application of quantum algorithms or quantum enhanced machine learning to solve quantum problems, is probably considered to be, let's say, the most promising by some researchers. But we'll see. So I hope that today we'll also learn about the state of the art, about some interesting applications of both quantum computing and machine learning and their intersections. So this figure was taken from another interesting talk about quantum machine learning with PenLA that was given by Maria Schult a few years ago during a talk during one of the Q webinars organized by QWORD. So now I will focus on this quantum enhanced machine learning, and here um, the main, let's say, building block are called variation quantum algorithms. So these variation quantum algorithms share a common structure where a task is encoded into a parameterized cost function, and that is called ansatz, and it's evaluated using a quantum computer, and there is a classical optimizer that tunes the parameters of the circuit. So these approaches have emerged as the leading strategy to obtain quantum advantage or to get any meaningful results actually on noisy intermediate scale quantum devices. So in this the famous NISQ area. So here you can also see a graphical representation of such a parameterized circuit that is responsible for calculating the cost function, and there is also a usually classical subroutine responsible for proposing better candidates for the parameters. So this was just a general diagram. So in general, this ansatz, as I said, parameterized circuit that prepares the quantum state. Some ansatz architectures are generic and they can be problem agnostic, but very often they are problem inspired, and in many cases we can use information about the problem to tailor an ansatz. So here on the left figure, we can also see a schematic diagram of an ansatz. So there is a parameterized unitary operator where we have a set of parameters that can be expressed as a product of some number of unitaries sequentially acting on an input state. And each unitary can be decomposed into a sequence of parameterized and unparameterized gates. And here on the right figure, we can see an example of such a decomposition. Okay, what are the required properties of the cost function that is computed using the ansatz? So its minimum should correspond to the solution of our optimization problem. It's useful to have the cost function that is operationally meaningful, which means that the smaller cost values should indicate a better solution quality and should be possible to efficiently estimate it by performing measurements on a quantum computer, and potentially with some classical post-processing as well. And there is an implicit assumption that the cost should not be efficiently computable with a classical computer, because otherwise this would imply that there's no quantum advantage can be achieved with these variation quantum algorithms. And of course, this cost function, the ansatz, should be trainable, which means that it should be possible to efficiently optimize the parameters. So it is a hybrid approach. It is a hybrid procedure. So there are some computations run on a quantum processing unit. Some can be run on classical processing unit. So the quantum processing unit is responsible for returning a set of measurements given a set of candidate parameters. And then the classical computer is responsible for calculating the energy value given a set of measurements from the quantum processing unit. And it's usually some kind of averaging of the results. So, and it performs the optimization procedure. So there are many approaches on how to do it. Here I just put some examples like stochastic gradient descent, Nelder-Mead method, and so on. But of course, it's very important which optimization procedure is chosen, because the choosing a right optimization method might decide whether we'll succeed or not. And there are no silver bullets here, as far as I know, but maybe our next speakers will also give some hints here. We'll see. We'll learn from their talks as well. So the classical computer also calculates what a new set of parameters should be. So it's a part of this optimization procedure. It checks the stop conditions, so whether we've reached the minimum and whether we should make more iterations or not. I mentioned that these variation quantum algorithms are especially good in the current, the so-called NISQ area, noisy intermediate scale, with noisy intermediate scale quantum devices. And of course, the question is why. So here you can see some main disadvantages of these NISQ devices. Like, there is a lot of noise. So every time we apply a gate or perform a measurement, there is a substantial chance that we'll actually apply a different gate, or the result of the measurement will be different than the theory predicts. And these are just some. This is just one of the many flavors of noise that we can get. And beside that, the qubits don't live for too long, so there is the coherence after some time, so we cannot be confident. So actually, after some time, we can be pretty confident that whatever information was stored in the system, it's already lost. So as a consequence, the number of operations, the number of gates that we can apply, the number of operations that we can perform is limited. And of course, we also have a limited number of qubits. Our contemporary quantum computers are still relatively small. And of course, there might be also some restrictions on which qubits can interact with each other. So this is also one of the limitations. As a consequence, we cannot use, so we can use only small number of operations per qubit. This is the so-called circuit depth, so the number of quantum gates that we can apply. We can assume that everything will go according to the plan and there will be no errors along the way. But even if there are errors, we should, design our algorithms in a way that we should still be able to get some reasonable answer, right? So we call this robustness. And obviously we cannot use more qubits than we have, right? So it's also obvious. So why these variation quantum algorithms are good for NISQ devices? So these algorithms are pretty flexible when it comes to the circuit depth. So initially we can use a pretty simple ansatz, that is a relatively shallow circuit. But once we have a machine which allows us to perform computations using a deeper circuit, we can use some more sophisticated ansatzes and performance might increase as a result. And what is especially interesting, in my opinion, is that these variation quantum algorithms have been shown to be somewhat resistant to noise. So even in the presence of noise, up to some levels, of course, it can still give the correct result. So this is this robustness that I mentioned earlier. And some people even claim that a pinch of noise might help with optimization process because it helps to escape local minima and might help with the generalization, because it's similar to something that is called a dropout in classical machine learning, when we intentionally add some noise to our model during the learning procedure, or there is also something that is called a variational dropout, where we can also add some noise, some randomness during the inference of the model that is already trained. And here I just give some examples of popular variation quantum algorithms like QAOA and its quantum approximate optimization algorithm and its variants like recursive QAOA, Wormstar QAOA, and variation quantum eigensolver and its variants like filter VQE, layered VQE, and combination of both. Of course, people started thinking about applying these techniques to enhance classical machine learning models like classical neural networks. So here, as you can see, an image from a talk that was given by Professor Piotr Gawron about quantum neural networks. So he gave this talk already a few years ago, but I think it's still quite relevant. So here you can see a combination of classical nodes, classical neurons, and quantum nodes. In this quantum nodes are just parameterized variational circuits. So here the parameters can be between different nodes, like in classical neural networks, we have parameters or weights of connections between neurons. But in this case, we can also have parameterized quantum gates. And when we train such a model, when we perform backpropagation, we know how to do it in the case of weights connecting the neurons in consecutive layers. We know how to calculate the gradient, but in case of this, quantum node, we can also calculate something like a gradient by slightly modifying the parameters. There can be also combinations of different algorithms. So here is just an example of an interesting master thesis that was defended a few years ago in Poland in the Kraków University of Science and Technology. Justyna Zawalka combined QAOA with a hybrid neural network. to solve the traveling salesman problem. So unfortunately, as far as I know, she was able to conduct experiments only on relatively small instances of the traveling salesman problem, like some toy examples, for several reasons. So the reason was how exactly the problem was encoded, what was the number of parameters, the number of available qubits. But in general, this kind of optimization problems in logistics are still quite challenging for the quantum computers, independently on which quantum approaches or hybrid approaches we try. There are also uh, methods that are called kernel methods. So also in classical machine learning, we have kernels. So in general, kernels map input data into higher dimensional feature space using a kernel function. So that it enables linear algorithms to perform nonlinear computations, right? And here you can see on the right some classical kernels, example of classical kernels, but in quantum machine learning, there can be also quantum kernels that are just quantum transformations in this case. Okay, so I've just shown some examples of quantum or hybrid neural networks, showed how we can calculate these quantum kernels for quantum SVM. So I can tell you that I've already seen in some research works hybrid or quantum counterparts of most of the popular classical machine learning algorithms. I didn't put it here, but even recently I saw some articles about quantum or hybrid large language models as well. So people really tried different approaches. So this area is being extensively explored, of course. But there is also another area that I mentioned at the beginning. So we can also think about applying the classical machine learning methods to enhance quantum technologies. But before we go there, maybe just a summary of where we are with this quantum enhanced machine learning. So I already saw some research works related to applying quantum machine learning or quantum enhanced machine learning for Earth observation, neuroimaging for Alzheimer's prediction. So there are already some research works about it. So if you ask a question, can quantum enhanced machine learning achieve good results in some learning tasks? The answer is yes. So there are already some demonstrations, experimental demonstrations showing that, okay, we can achieve good results for some learning tasks, for some learning problems. Not all, definitely. But if you ask a question, can quantum enhanced machine learning outperform classical machine learning? From my perspective, based on my knowledge, perhaps. So we are not really sure. So one perspective, it's probably still too early. So if there are some experiments demonstrating some advantage, they were usually some small scale experiments, and it's difficult to prove that it's really quantum advantage in this case. But it is the same with many things in machine learning. So even in classical machine learning, when we see a new model applied to a given task, we can be almost certain that there exists a better model for this particular task. And we can also see it based on just monitoring the development of the classical AI field, where we see that within a few weeks, there are usually better and better model released that already outperform the previous state of the art. It's similar in classical machine learning. When we have a single classical machine learning model, we cannot be sure that this model is really the best possible, and at least it's almost impossible to prove for an arbitrary data set. But it's for sure it's an interesting research area. Definitely, there are many interesting research works. And now going to application of classical algorithms to quantum data. So I will just give some examples and give a reference to an interesting review article that was published a few years ago. So some examples like quantum state tomography. It's a process by which a quantum state is reconstructed using measurements on an ensemble of identical quantum states, and quantum feedback control and quantum circuits optimization. So usually So in these particular works, as far as I remember, people applied classical reinforcement learning to, enhance these quantum approaches. If you are interested in more applications, there is a nice review paper that was published a few years ago about modern applications of machine learning in quantum sciences. And I also wanted to mention one interesting research work related to this domain as well that I'm also focusing on in my research. So a few years ago, there was a very nice paper published. The title was QROS, Cubo Relaxation Parameter Optimization via Learning Solver Surrogates. So in general, when we have some optimization problems that we want to solve using our quantum algorithms, we usually formulate this problem using something that is called the Cubo formulation. So it's quadratic unconstrained binary optimization formulation that corresponds to a Hamiltonian of a certain physical system, and we can, in some sense, employ the nature quantum mechanics to help us solve this optimization problem. And usually in such formulation, there is a part that we want to really minimize, that is our objective function, and there are some parts corresponding to satisfying the constraints. And usually there is a parameter that in this case is called the relaxation parameter, that is a coefficient regulating the quality of the results and the probability of obtaining correct results for quantum computing. So it basically is a trade-off between satisfying the constraints and achieving high quality solutions. So if the value of the parameter is too high, then we can be sure that the candidate solutions found by our solver, quantum or classical solver, will satisfy the constraints, or at least it's very likely that they will satisfy the constraints. But it can be more difficult for the solver to find really good results for the objective function. On the other hand, if the value of this parameter is too small, then it's easier for the solver to find good solutions, but we cannot be sure that the solution that we find satisfies the constraints. So there is a balance, so there is a trade-off, and we need to find a parameter, relaxation parameter, that could be a good balance between the quality of the solution and probability of achieving a feasible solution. And here classical machine learning can help with this, because in this QPOS paper, the authors first solved some instances of the traveling salesman problem for different instances of the input graph and different values of the relaxation parameter. So they got the probability of obtaining a feasible solution, the average energy, so the average quality, and the standard deviation of the quality of the solutions. And they trained a classical machine learning model that in this case was a graph convolutional neural network, because there was an input graph that for a given instance of the traveling salesman problem and a given value of the relaxation parameter return this probability, expected value of the results, and standard deviation. To summarize, here we use classical machine learning to estimate the probability of obtaining a feasible solution and the estimation of the expected quality of the solution. And once we have such a trained model, for a new instance of the input graph, for the new instance of our optimization problem, we can just test different values of the relaxation parameter, put them as an input to assess this probability of getting a feasible solution and the expected quality of the results. So this was a very nice approach, and of course, I believe that most of you are interested in answering the question whether we already have a quantum advantage in case of quantum machine learning. So it's as I said in one of the previous slides, it's probably still too early, and it's difficult to prove that we formally mathematically prove that we already have some advantages. But I wanted to just show you some examples that were published just recently. There was a publication of a research conducted by Google a few years ago. And so there was a title, as you can see, Google researchers find potential for quantum advantage in machine learning tasks. So now they said this is just a potential for quantum advantage, not the quantum advantage. And here you can read that the study showed that quantum machines could learn from exponentially fewer experiments than the number required by conventional experiments. So the advantage is not in terms of the accuracy, but in terms of the size of the data set. And this is also very important because sometimes it's very difficult to obtain a very large data set. And the exponential advantage is shown for predicting properties of physical systems, performing quantum principal component analysis, and learning about physical dynamics. The researchers write. Another example, this time, as far as I remember, it was, yes, it was in 2024. There was a paper about an in principle superpolynomial quantum advantage for approximating combinatorial optimization problems by computational learning theory. Yes, so here they provided special instances that are hard for classical computers to approximate out to polynomial factors, and they gave a quantum algorithm that can efficiently approximate the optimal solution within a polynomial factor. So it's also another kind of advantage. Here another publication about generative quantum eigensolver, so generative quantum AI in this case, by using quantum systems to generate data, and they used AI to learn from and guide the generation of more data. And then they create a powerful feedback loop that enabled breakthroughs in diverse fields. So this is what was claimed here. There was also a publication from IonQ. There were some new hybrid quantum algorithms. Yes, hybrid quantum classical approaches that enhance both large language models and generative AI. So you can also read more about on the website of IonQ. There was also another interesting application. So here, this time from China, Chinese scientists used a quantum computer to fine-tune a billion parameter AI model, marking what they claim is a global first and step forward toward combining quantum computing with advanced AI tasks. So of course, there can be a lot of hype here as well. And as I said, sometimes it's a lot difficult to verify some research works, but you can see that there are already some papers claiming that we can, or at least there is a potential for some quantum advantage. This is just one of the recent papers from 2026, Exponential Quantum Advantage in Processing Massive Classical Data. So Hartmut Neven was one of the co-authors. Yes, and here you can see that yeah, classical machines that are exponentially larger yet below the required size in superpolynomially more samples and time. And they validated quantum advantages in real-world applications, including single-cell RNA sequencing and movie review sentiment analysis. Okay, and then they said that these quantum advantages are enabled by quantum oracle sketching, an algorithm for accessing the classical world in quantum superposition using only random classical data samples. So you can see that some research works co-authored by famous serious researchers already claim some advantages, or at least potential for advantages of applications of this quantum enhanced machine learning. And finally, just to wrap up, examples of some quantum machine learning frameworks or libraries, if you are interested. PenElane is probably the most popular. So it was the first quantum machine learning library at that time at the time when it was published. It was called TensorFlow of Quantum Computing. Until Google released its TensorFlow Quantum library. So there is also such a library for TensorFlow. There was also a machine learning model in Qiskit, Qiskit ML. And if you want to learn more, here I give some links and references to some resources that can be hopefully interesting for you. There are more sources on the website of the Quantum AI Foundation. And with this, I would like to thank you for attention. If there are some urgent questions, I'll be happy to answer, but I see that we are already slightly delayed, so we'll soon move to our next talk given by Sven. Let's see, I will check on the chat if we have some questions here. Okay. the person is doing research application of VQE and have challenges running some LAMP packages, cannot use packages. If there's any platform that can assess, maybe Amazon Braket, I don't know. So perhaps you can just try to run it in the cloud if your laptop is not strong enough, or just perhaps you can try to. It's usually good to try some cloud services in this case. And there's a question, is QML will always be potentially, when can we get to say always better? I believe that we'll never say always better. I believe that in some cases we'll say that, okay, it's better in some cases. But it's for now, it's not very likely, I think, that we'll say that it's always better than classical machine learning. And one of the reasons is also that, contemporary classical computers are very powerful, especially graphical processing units that we use to train classical machine learning models like large language models. But regarding this question about potentially better, so I already, showed some papers, some articles claiming that we already have some advantages, at least in some very specific cases. Regarding the certificates, no, we do not give certificates for participation attendance. So the invitation email can be your, let's say, certificate. There are just too many participants, sorry. When we do some workshops and there are some quizzes at the end, assignments that we can grade, then we can issue certificates, but not for participation. Okay, I do not see more questions now. So if there are some other questions to me, I'll be happy to answer on the chat. But let's move forward and let's welcome our next great speaker, Sven Groppe. So Sven, thank you for accepting our invitation. Thanks for being with us. I'm not sure if you can already share your screen. If not, I will try to enable the screen sharing. First, I will stop sharing my slides. And let's see.
Yes, you must activate it.
Yes, okay. You should be able to share your screen now.
Let me see. Yes, now I see it. I hope you can see the screen.
Yes, I can see it. Great.
Yeah, great. So thank you very much for the invitation to give here a talk. You see my slides, data quality in the era of quantum computing. That is also a big topic right here. I will maybe just go very much into the end to just show you in the beginning that there's also further reading. So the talk is based on a tutorial which we have given last year at the EDBIS conference. There's also some accompanying paper right here. And also we have an updated version, so to say, at the QData workshop in conjunction with the top-ranked SIGMOD conference right here. The DOI still, I think, doesn't work. It should be published soon right here, but there's also an arXiv version out there. So if you want to have more information about it, maybe that is the source to go to, besides all the references which are given in the paper, especially here in this one. Then going back to the beginning, so the agenda for today for my talk is that I first give an introduction into data quality in the classical world, and then show also, okay, some have already mentioned it, that we always speak about potential. Then I will also show the potential of quantum machine learning, especially, but in general, quantum computing for this area of data quality. We have, quite many data quality dimensions. So most researchers in the data quality community say the super concept or super dimension is fitness for use. So we check the data quality or evaluates the data quality for the fitness for use. And because it's a super dimension, you have a lot of concrete instances of it right here by, then going to so to say, to the application right here, to the use cases. And in this way, we have a lot of more dimensions, which maybe you are familiar with: accuracy, concise, completeness, and so on. So many researchers say there are about 16 or 20, whoever you ask, most important dimensions. Here we have the result of a very old survey paper from 1996, and they already collected 179 dimensions to measure data quality right here. And so you see it's a big field, and today, of course, there will be many, many more data quality dimensions out there, which are referring to today's use cases, to LLM area. So if you process natural language text, you might have many, many more data quality dimensions, for example, to measure the quality of natural language text. Okay, but going back to the roots, right here, of course, it has been an old topic in the database community. They especially looked, for example, in the first time about data quality in relational databases. So for example, here we have the example of a hospital patient records. And then, of course, you can see that even in one table, and maybe, of course, you should evaluate the whole database with several tables. You can see that there are a lot of data quality issues already inside. So here the null value indicates a missing value, so that refers to the completeness dimension. Right here, you have conflicting values and duplicates. It refers to or relates to the consistency dimension for data quality. And maybe you have incorrect values, which here refers to accuracy. So for example, the wrong blood type has been recorded right here. So, and this is also only a small number. So you see, it's not so easy to just pick one dimension. So even in some data, you should look at many, many dimensions right here to have an overall view on the data quality. Of course, you just don't want to only assess the data quality. So data quality assessment, were based on a selected subset of this data quality dimension. You evaluate the data to identify issues and understand the data. You also want to do some actions to do data quality improvement. So improve the data quality by modifying the data values to meet the quality targets, by applying some corrective actions. And again, then after you have done that, you can verify that there is some success in data quality improvement by rerunning the data quality assessment again. And in this way, iteratively, you improve the data quality right here. Data quality is a big field. Maybe you already get an impression of it, but you can also look that the data quality field has been altered, has been evolved over the different research areas of data management. So for example, in traditional data management, you always had this fixed schemas of relational databases. You have structured local data. You look for this data quality dimension, which I said before: missing values, conflicting values, integrity violations, and many more. If you look at the area of, and of course, that time has not been over. So always to say, okay, relational databases are there and they will survive, I guess, at least my speculation, for a very, very long time, and maybe they will stay as long as human lives. But that is only speculations. As well, the same for big data and machine learning and so on. Of course, the old techniques will remain. So for big data, the main issues were that we looked at heterogeneous, we now had heterogeneous large-scale data, big in volume, big in variety, big in velocity, and so on. So you also wanted to do that, or always want to do real-time answers right here. And in this way, you have to process is distributed, and also you collect the data in the distributed environments by having many, for example, sensors and so on, who all contribute a lot of data, a lot of users in social media and so on, who always send some posts. So your data is constantly evolving, becoming bigger and bigger over time. So the data quality challenges have been especially that you have trade-offs between efficiency and accuracy, that because you look at so many sources, you have to look at the trustworthiness of the sources. And as I already pointed out, maybe you have real-time quality constraints, even in this situation where so many new data comes in. And of course, now we are still in the machine learning area, and maybe LLMs, agentic AI is missing here on the right. And for machine learning, we have dynamic high-dimensional data. We have a multi-stage pipeline. So we have different stages like data preparation, training, and then deployment and using the trained model, and you have to monitor it, and if it still works good or if there's some drift in the new data coming in. And of course, if you consider this, training data, for example, you must look if the data is fair, if there's some bias inside. You should avoid bias inside. You should somehow take measure such that it is fair. Right here, there might be some data drift, so the data changes right here over time. There might be some label noise, so some labels might not be white inside. And of course, because of this big data, very often you go for weak supervision or no supervision at all right here for your systems. And with large language models, agentic AI, you couldn't have some data quality challenges like hallucination right here, especially like this. And you come now much more to process natural language text, which you should consider right here. And with agentic AI, where you have agents based on LLM in a complex multi-agent system, then there might be also some situations that some unfair conditions, for example, or bias will amplify right here through the whole system. That has been also shown, so you have to take measures about it. So the whole area of data quality is much too big, so we should focus on some certain aspects. And one of the most important one is detect anomalies, because many data quality challenges manifest as anomalies. So we can look at outliers, so values that deviate strongly from the norm. So we should check them. If there's something wrong with them. There might be errors right here, so wrong or corrupted data entries, which might be detected as anomalies. There might be fraud inside in financial transaction data, which might be seen as anomaly in comparison to the normal services usage in these transactions. There might be failures, so abnormal system or sensor behavior. There might be low quality records, so incomplete or unreliable data. So we can look at anomalies. We can ask what is an anomaly first, because maybe for you it's quite obvious, but if you look at it in detail, it might be not so obvious. So simply speaking, that is just data that differs a lot from the rest. So anomaly is a pattern in the data that does not conform to the expected behavior. And sometimes you have other words like outlier, exceptions, deviant, and so on. So maybe with some nuances in the meaning in comparison to anomaly, but in principle, they refer to similar concepts right here. And but you must always think about, okay, is it an anomaly in this way that you don't want this data in the data, the anomaly, or is it a rare event? And yeah, you want the rare event in the data because it's also normal data. Okay, there are different types of anomalies right here. So even if we focus on anomalies, we can look or must look at the data. There's time series data. First, looking at univariate time series, that means that we have only one signal. For example, an ECG signal, there might be different anomalies like point anomalies. So an individual data point seems strange when compared with the rest of the data. So here you have an extremum right here. So maybe in this case, if you have here an extremum, it might be a failure of the device, and that might not something like a heart attack or something like that. But we should check if the device still works correctly, or if it was just changed to another patient or something like that. Okay, but there might be also collective or subsequence anomalies. That's here on the left shown. So a collection of data points seems strange when compared with entire data set, although each point may be okay. So if you look at each point, there is no extremum right here. So it's in the range, in the typical range. But if you look at it, we have here an altered rhythm, higher frequency, and it looks like immediately the doctor should arrive to check for the patient right here. Okay, but there might be also other situations, applications, data, for example, where you not only have one signal, but many signals right here, and you can also look at the correlation between these several signals. So in this case, we have two signals, and more often, at least, we have an anti-correlation pattern. So if the blue line is up, the red line is near zero, and the other way around, something like that. Here, right here, we have some subsequence where suddenly the blue line and the red line are in phase. And yeah, that seems to be strange in comparison to the other situations right here. And that might be some hint for the device is going to be out of order or something like that. So predictive maintenance, you could go for checking the device if all is working correct, something like that, or whatever data you look at. Okay, we see, okay, even if we look at anomaly detection, there are different, many different anomalies. That is also only some few of them. So if we define the process of anomaly detection, we would say, okay, it's a process of identifying data points, patterns, or events that deviate significantly from the expected behavior. We can have binary output just saying, okay, that's normal data, and now we have here an anomaly. But yeah, in general, maybe it's more preferred that there will be a scoring output, so a real valued score or rank right here saying, okay, from 0 to 10, if it is 10, then it's an extreme anomaly, and if it is 5, then it might be an anomaly, it might be normal data, we are not sure about it. And then maybe, yeah, the stages behind it might have some thresholds and say what to do here or there. So the overall goal, of course, is always to separate normal data from irregular and abnormal data. As said, we have various applications like in finance, credit card, insurance frauds, market manipulation, money laundering, which can be all detected with anomaly detection. In healthcare, we can detect diseases on medical data. And for example, we can detect heart attacks, cancer, and so on. And in the cybersecurity domain, maybe we can go for intrusion detection. So if there is abnormal network traffic or unauthorized access, we can detect malware, botnets, insider threats, and so on. And you see, it's all about money. So if only some few percentage you improve anomaly detection, then you can save a lot of money in your company, or maybe you can save even life in the healthcare domain. So it's very, very important to work on that. If you look at the different methods, they are in line with the different methods in machine learning. So we can have supervised anomaly detection where labels are available for both normal data and anomalies. Of course, there we have very imbalanced, typically very imbalanced data sets right here. So because the typical assumption is that anomalies are very rare right here. So the anomaly class for this, you have only few examples, and for normal data, you have many, many examples. You have to do the methods for imbalanced data sets. Very often you look at semi-supervised anomaly detections. So labels are available only for some normal data. And so maybe the anomalous has not been detected so far. And your approach should look for it. And you can have unsupervised anomaly detection approaches where no labels are assumed right here, and you can do some clustering and this stuff to still detect some anomalies. You can look further, of course, in detail at the different methods. Can have statistical, distance-based, clustering-based, classification-based, reconstruction-based, prediction-based, informatic, theoretic methods right here, and you have a lot of different approaches out there, and for some, Pavel already pointed out that there's some discussion that we have quantum advantage right here. Okay, so the landscape is manifold, even if you only look at the classical world. So here we have a survey from 2022. It's a experiments and analysis paper. So there's a been collected 158 anomaly detection methods for time series data. I think they have in the evaluation something above 60 anomaly detection methods they compared in the experiments, and the result was that no algorithm or algorithm family clearly dominates all other approaches and solves all anomaly detection setups. That's very interesting. So even in the classical world, you cannot say, okay, I have a new use case data and I know exactly which approach will be the best for anomaly detection for my data, for my data set, for my use case right here. You know some tendencies, you can check the paper for it, know the tendencies, and there might be some selection about some approaches which are quite good and that you can compare with. But overall, you can't say for your use case, for your data set, which is the best one. And here I will say, okay, the situation will not change if we also look at quantum anomaly detection, if we bring it into the play here. So for some data sets, for some use cases, it might be a little bit better. For some others, it might be worse. For some others, it might be comparable, have comparable performances. Okay, but I've already told you, even if you have small improvements, it will save much money in the company, it will save life and so on. So we always have to look for it, and that is also a promise that we don't have to look at a clear quantum advantage right here. We can consider it as also some tool like the other classical anomaly detection approaches, and can just choose the or test some approaches, also some quantum anomaly detection approaches, and sometimes it's your preferred choice because it is a little bit better than the other. So we don't have to claim we are always better, or we will be anyway much better than the classical approaches. Okay, key challenges, looking at the time, I will jump over, especially one key challenge is that most approaches are computationally expensive. So quantum computing must make sense for looking at the data quality area. Of course, now we can check when do quantum approaches make sense. Right here, there might be some approaches where quantum subroutines do not make sense, because in the classical approaches, you have too simple calculations, or you have too efficient classical approaches right here. That might be the case. We must live with that. There might be the case where we have a quantum variant of the quantum anomaly detection approach directly. Right here can already have the research about quantum machine learning. We have the specific quantum machine learning approach already is there, or quantum computing approach if you also look besides quantum machine learning, and we can directly use it for anomaly detection. That there are also some examples for it right here. We can look for approaches where you have classical approaches, and there are some subroutines where you can just replace the subroutines with quantum drop-in replacements. so to say, with quantum approaches. So you have this hybrid quantum classical approaches applying there. Okay, there are many approaches for it. I will present some in some taxonomy. There might be approaches where promising quantum variants might be missing, which can be used as quantum drop-in replacement. But maybe there is nearby research, so the exact variant is missing, where you could directly use it in your as hybrid approach in the classical approach right here. But because you have nearby research is already there, so most probably there will be shortly, or it's promising to look at these approaches and do research and even invent or these approaches as direct quantum variants right here. And of course, you can always discuss, okay, what is a real quantum Ani detection approach, which is neither inspired from classical approach nor classical variants would make sense of it. And if you look at it in a real pure sense, in a very strict way, maybe you could discuss or argue that no approaches of this kind in the moment are known or not. This might be a discussion for the night or something like that. Okay. So to say, of course, we can look at the potential of quantum anomaly detection at the speed ups. We know that a lot of approaches in theory have quadratic speed ups or have even exponential speed ups. Here are, we can give also the reference for it. Here are the approaches which can be used also for data quality, but always you have to think about the important K-feeds like overheads for classical data loading and quantum error corrections. That can limit the applicability of the quantum methods. And so depending on the application in data sets, overheads may even arise any speed ups, if not, and quite often also the quantum approach is carefully designed. So you must always also check the papers if they claim it in theory and maybe also in practice, but might measure not all of the preparation steps right here. So you must always look at it in detail if in practice this speed ups will be achieved or not. Pavel already pointed out a lot of potential of quantum machine learning. So the general tendencies are that with much less parameters, that has been shown, but in many papers and studies, you can achieve comparable or almost the performance of classical machine learning with a lot of more parameters right here. So you have less memory footprint. That no discussion about it, but you don't beat quantum machine learning, or quantum machine learning don't beat classical machine learning in many studies right here, and only in some it even beats them. For some data, we have more compact representation, so logarithmic number of qubits in comparison to classical bits. So with that, you might have faster convergence, less training data. It's more generalizable. Less training data is a very big point right here that has also much costs in companies. Okay, but overall the advantages are contextual, so they are clearest for quantum native data or when you efficiently prepare and encode the inputs on the quantum device right here. But overall, this of course is topic of open research right here, of current research right here. And looking at here the small number of parameters used already, we actually do not know what happens if we use a very high number of parameters in quantum machine learning. That I just want to point out here. And to reach that, of course, we must look at the current quantum computers right here, still in the NISQ area with one step in fault-tolerant quantum computing, I would say. Here we have the timeline of different quantum computers with the number of qubits right here, and the agenda is promising even for fault-tolerant quantum computers. That's very interesting. We have a simulation ball, even if we don't want to look at quantum computing, real quantum computers so far, check it theoretically with simulation. We see that we have limits, something above 50 qubits cannot be simulated anymore, only if the circuit has limited entanglement, connectivity, or shallow circuit depths, or both, then maybe we can go over it, maybe some hybrid approaches, but overall there is some limit in simulation. So we need to wait for the big fault-tolerant quantum computers to see the if more parameters have much better results. And there's a data and use case wall. So even if we can go for much parameters, we must always ask, do we have enough data for training, such that the model can be trained enough to be general enough. And for many, many domains, we are running out of data for example, training LLMs, but also other domains. Then we must check, okay, is the data of high quality? Of course, we want to go for data quality here, but for training, the data itself must be also already of high quality. If there's much noise inside, then that hinders better predictions of learned models. So there, we need data quality improvements right here to even have data quality to train the models better right here. And based on the use case and the data, which is the best performance we can get? So is there an inherent limit of the performance right here of prediction? So, and is this inherent limit already reached with classical machine learning? So that's also an open question. I don't know if we can measure it, or I'm pretty sure that in the moment it's always the best results of the best machine learning approaches are reported, and we don't know if we can get above that. So I think my time is already over, so I will go a little bit above that. We also did some survey about the classical anomaly detection approaches right here, which could have directly drop-in replacement of a quantum approach. So we replace a classical subroutine with a quantum subroutine right here, and then we could run it. This work has not been done, but we identified the classical anomaly detection approaches for it. And here on the left, we have the taxonomy of the quantum machine learning approaches. And we see, I think it was something over 40 approaches, so much potential is there. And we also check, okay, which quantum anomaly detection approaches have been already there. And this is this one. We have also here the taxonomy of the quantum computing approaches there. And we see just by comparing the taxonomies and so on, and even not going into the details of each approach, that there are still a lot of differences. So there's a lot of potential for future works right here. And with this, I want to close it by just mentioning that, of course, anomaly detection was only one direction of research in data quality. There are others like data cleaning, deduplication, schema matching, and so on. And similar, pretty the same, we can make an investigation with quantum approaches could make their benefit. So overall, we can say that realizing quantum enhanced data quality requires overcoming these barriers through concerted research efforts. It's an interdisciplinary field which requires close collaboration among quantum physicists, data scientists, and database engineers. So unlocking the full potential of quantum enhanced data quality hinges on bridging theory with practice and addressing these key challenges right here. Again, I just want to point out there are papers available, and here's also an archive version of it because it is short for publishing, but it's not published so far. And this one is the older version, which doesn't have so many details as the first one. So I refer that for further reading, and I'm open for questions so far. So I will stop.
Okay, great. So first of all, Sven, thank you for this great and very informative presentation. So thank you. I see some questions on the chat. So one is quite general about data preparation for quantum machine learning compared to classical machine learning. I already answered on the chat that probably the main difference is in the way how data is encoded. But perhaps you can tell more, or maybe you know some other differences.
Yes, so my presentation was about classical data quality, so data quality with classical approaches, with classical data right here. And then, of course, we have all these issues with data loading into the quantum computer. We must think about the data encoding itself. So all these variance, angel encoding, amplitude encoding, and so on we can use. And if we have many data items to feed in, there might be also approaches like block encoding, which you might look at. That is one thing that is the same as for all the other things in classical machine learning. But what I left out, I didn't clarify it in the presentation. What I've left out is to look also at quantum data. So if you have quantum sensor, for example, you can measure quantum data and so on, and you could make there also think about how to improve data quality for quantum data. And with that, maybe you could more or less directly use the quantum data in the approaches right here. But the typical main applications are in classical data quality. So far in companies and so on, there are some, I would say, niches, but maybe they're still very important right here where you can look for quantum data. I hope that answers your question.
Okay, good. Thanks. There are two other questions, perhaps not very related to this talk specifically, but we'll see. What domain, like image, sound, and so on, use case application for quantum anomaly detection from paper? I'm not sure which paper is.
So
mind,
it's a big field, and of course it can be all. In general, in the presentation, especially in the classical part, I showed time series data right here. So the survey with this 158 classical approaches, that was mainly about time series data. But of course, we can also look at images, sound, videos, and so on. So, and also multimodality. So different modalities could come into the play if you have images right here from for example, from a traffic control. So maybe one of us drives too fast and gets a photo from himself, and then there might be, the police might check if one says, okay, I was the one person who drives it, because it just sending this to your home, and you should say, okay, this one is there, and maybe someone said, okay, I have so many, I've done this before, so maybe you could take this duty over, something like that. And then the police could just have the image and have classical data like, okay, what's the gender of this person, what's the birthday of this person, and then it might check, okay, does this fit together, or is there an anomaly? Something like that. So
Okay.
multimodality, just an example. There can be many more examples. Multimodality could come into the play right here.
All right, great. And there's another question. Is DC a way to see if data is reliable or to find anomaly? I don't understand how it is related to QML. Is DC for QML different than classical ML?
Yeah, so DC maybe it means data quality. I don't know exactly
Perhaps.
what DC is referring to, but
Yeah. Maybe the person can, this was Nizamuddin. So Nizamuddin, maybe you can unmute and clarify because it's not clear for me. Data
data quality.
quality. So
It
it should be
just sends
DQ.
in the chat. Yes. So data quality is just a typo right here. So as already point out, we have to check for example, a data point right here. Is it an anomaly or not? So is it something like normal data, or is it different from the normal data? Is it different to the expected data what we want to have here? And this anomaly might be a hint for some data which you don't want. And with that, you can apply the techniques of machine learning right here, supervised, unsupervised, and so on, semi-supervised, and so on. And of course, there are also some counterparts in the quantum machine learning part here. And the quantum machine learning parts, where it is different, is more in the techniques applied. So you could say, okay, in quantum machine learning, in simplified speaking, very often you just replace a classical model with a quantum circuit and train then the quantum circuit as model to have some, after you post-process the measurement to have then some prediction of your data, of your input data. And what's different than to classical machine learning is that you have to encode the data right here with quantum states that you have to think about, that we discussed quite in the beginning of the Q&A for this presentation. And also in the data encoding of, in the end, and how to interpret then the result right here in the end. So the measurement. So very often there is some post-processing needed to interpret it in a, in a way right here. And with that, but that is the normal difference between machine learning and quantum machine learning. I would say.
Great, thank you. Thanks for the answer. Yes, so I think that's. I don't see more questions now. So Sven, thank you again for the presentation, and let's move to the next talk. Artur Miroszewski is our next speaker. So Artur, if you are ready, you can start sharing your slides.
Yeah, I think I'm ready. I'll just
good.
I guess you can hear me, right?
Yes, I can hear you. Yes.
I'll try to share a correct window. Hopefully you can see. Can you see the slides?
Yes, I can see your
good.
slides.
And now it's full screen, right?
Exactly, yes.
Great. One additional question. Can you see my mouse cursor right now?
Yes, I can see it.
Excellent. That's excellent. So maybe I will just start.
Okay.
Sorry, I actually haven't unlocked my camera, so maybe it would be a little bit. I don't want to be rude. So hello everybody, and I will start sharing again. Hopefully everything works. So yes, good. Well, still good morning, everybody, at least in Europe, test time. My name is Artur Miroszewski, and although the title might look a little bit intimidating for today, I guess that actually it's a thing I've been working for a couple last months between different responsibilities, and actually it's very focused, almost engineering-oriented problem that although we have a very specific problem and a very specific solution, I hope it will also convey some more general message. And actually, I will spoil this message already from the beginning. The message is that almost always when we think about near-term quantum machine learning, we use hybrid algorithms that use some, they're very close to quantum routines, machine learning routines that we know, but somehow they do differ in some small points. And usually those differences, are really interesting and hopefully can give us some kind of a, not advantage in the sense of quantum advantage, but we can use it for having some better results or better setup of our routine. In this case, we'll focus only on quantum kernel supervector machines, but I believe it's very well. The whole statement is much more general, and we will see how it looks on this specific example. Maybe I should also introduce myself instead of just introducing the idea of the talk. So, as I said, I'm Artur Miroszewski. I'm currently research fellow at the Center for Earth Observation in European Space Agency, and my responsibilities are to lead and perform quantum activities in the department, which is so-called PhilLab, and it's devoted to investigating the innovative and disruptive technologies, computational paradigms for applications in Earth observation. Okay, so that's my affiliation, and with that, I think I can proceed. As I mentioned, the very specific topic will be that I'll present is related to supervector machines. So I guess many people know what SVMs are, but nevertheless, we should have some few words of a proper introduction. And supervector machines is a machine learning routine or machine learning algorithm, one of the classical ones, which was very popular, I guess, in the 90s and early 2000s, before the neural networks took off. And it's a classification algorithm that tries to separate points with different labels by placing a hyperplane between them. In general, if it's possible, then there are infinite number usually of hyperplanes that you can put between two sets of data points which have different labels if they are separable. But the very specific goal of support vector machines is to find such a hyperplane here, visible here, that maximizes the so-called margin, so the distance from the perpendicular distance, if we can define it in this way, from the hyperplane to the nearest point from each of the classes that we have. And this is a very nice visualization how this algorithm works. However, by itself, if we would only introduce linear hyperplanes, that algorithm would have very restricted use because not many datasets are linearly separable. So one of the biggest breakthroughs in SVMs was introduction of kernelization, or using kernel SVMs, in which for the linear part in the algorithm, we use standard inner product between data points to reach the optimization goal that we're looking for. But somehow, if we replace it with the standard inner product with some other function, I will not right now describe all the mathematical properties, but if we replace this inner product with some function that have some nice properties, actually we can introduce some mapping of features with which we deal into higher dimensional space, usually higher dimensional space, and also within this mapping, we can introduce non-linearity to the system, and in the end, classify points that are linearly non-separable. It's, I guess that the popularity of supervector machines lies exactly because in this kernelization, that we can actually use it for also very complicated data sets. And although we don't need that much to understand the decision function from this formulation, I would like to just indicate one thing, this alpha coefficient here. And yeah, okay, maybe one more thing. To find the margin in the, let's start with hard margin version of the SVM, we basically look for points that are, well, closest to the hyperplane, and they are called support vectors. And in this case, only those points in the end matter. They define the classifier. All the other points are unimportant. They are, if we already identified those support vector points, all other points can be, let's say, erased. We don't have to take them into account. And there's also more popular version of soft margin SVM, where usually it's not a single point defining the margin, but the points which are very close to the margin. So in this case, it would be with the blue points with soft margin, the biggest influence on the classifier will have this point. The closest one to the margin is, I guess, this one. So probably this one will also have some influence. And well, points at the back will not have influence at all. So we can see already that there's some kind of a structure in this problem, right? And not every point is as important as the other one. And actually what alpha tells us, the so-called dual coefficient, the value, well, the absolute value of alpha tells us how important the point is, simplifying a little bit. Okay, but what does it have to do with quantum? Actually, a very popular approach in near-term quantum machine learning is so-called quantum kernel SVM. It's actually taking the classical routine, but obtaining this kernel function with the use of quantum machine. Okay, so usually this is the definition, how we use the so-called fidelity kernel. And what is really important, that's actually on the next slide, so I will maybe go further, is the difference how we obtain those functions. And in general, if we want to compute some function, let's say classically, well, the function value, classically, we define the function, delegate it to CPU, GPU, and obtain the function value. It's a single deterministic value. A function is evaluated just once, and basically the error of our computation is limited only to well, the floating point precision that we use, and it's basically negligible in most cases. And somehow the representation for computing functions on a classical computer, I would say we use very precise calipers on which we can measure only once the function with a very good precision. On quantum computers, it looks a little bit different. We, let's say, implement the function as a quantum circuit, and we are now focusing on the fidelity kernel. We perform measurement, and for the fidelity kernel, this function, we obtain zeros and ones, or even 0 or 1 for each measurement. And in order to infer the actual value of the function, we have to repeat the measurement or the whole circuit many times, n times. And what we do is, if this x is the outcome of the single measurement, 0 or 1, we take the average value of the of x's. And this is basically they come basically from Bernoulli distribution. So it's P is a probability in a binomial distribution, but the most important thing is the error here scales with the number of measurements that we perform. The better precision of a function value we would like to get, we need to allocate more and more measurements, and currently using quantum computers is really costly, right? So we really have to be aware that the additional accuracy comes with some additional resources that we have to use. Why is it important? Well, because in kernel methods, well, the classical kernel methods assume exact Gram matrix. This is not the case for quantum kernel methods. And in quantum kernel methods, well, each coefficient of the matrix is an estimation problem, exactly the one I have here on the in the middle of the slide, with finite shots. And if we think about it, well, actually kernel estimation by itself is not a goal, okay? We just need this kernel value, or the kernel matrix, in order to feed it into some downstream task or the downstream classifier. And in this case, well, the SVM model. Okay, and one other observation is we have it's a kernel matrix in the end, because we compute similarities between pairs of data points. So we have many kernel entries, and as I mentioned before with this comment about dual coefficient, not all are of equal importance. Okay, and there's one more observation. Shots, well, when we perform the measurement, the quantum kernel estimation, shots are usually sequential. Okay, so from that you can get some kind of an idea that, well, this is completely different how we estimate function with a classical computer, and this sequentiality and thing that we are estimating many functions at the same, well, for the same task, means that there's some kind of a time, well, maybe not time, but we can somehow uncover some information already while being in the middle of the whole measurement batch. Okay, and what is currently I think that's okay. Yeah, that's on the next slide. Sorry for the animations. I'm really bad at PowerPoint, but somehow I'm forced to use this template. So restating what I just said, we in quantum SVM methods, we have some classical data, or quantum actually, let's say an image. We try to estimate kernel matrix on a quantum computer, which is probabilistic machine. We are basically throwing a coin or a dice, and then we feed it to classical routine. Some points are more important, some points are less important, and it really depends on the matrix that we have estimated. And what in most cases, well, what's usually and basically always done when we talk about quantum SVMs, people devote, this is a representation of the matrix, the same number of shots to estimate each of the kernel entries. But honestly, it doesn't make sense in my opinion, because we know that not all points are equal in this setup. And if we somehow are able to guess which points are more important than the others, then maybe we could devote much less points to points that measurements to points that do not matter, and much more measurements, and also much better. So we obtain much better precision to points that actually matter. So let's use a Google Maps analogy. I would say that the standard approach is the uniform strategy that everybody uses. It's not really good in my opinion. It's very costly. Okay, and well, what I propose is to use an adaptive strategy, just because how quantum kernel estimation is defined, right? We can do this, and in this way, well, not many people. I guess that it's a completely novel approach. I will have a comment about it. I guess it's quite good and it's much cheaper. And I will give you results and the whole algorithm structure just soon. But I wanted to just mention, so what tasks? Okay, we know that during the subsequent or sequential measurements, we'll uncover more and more structure in our matrix. But the question is then, okay, so how would we like to, we assume that we have some budget for our shots, the total budget, and how can we distribute the shots for each of the kernel entries? And I would guess that, well, there are many ways to define the allocation strategy. And the one that I propose, but it's not universal, is to look at the classifier geometry. Okay, so what I assume is that somewhere in the Platonic world of classifiers, or basically a state vector simulations of the classifiers, there's the exact kernel matrix. It's the limit of infinite number of shots, and we would like to recreate within our adaptive scheme as best as we can this matrix, and for example, or this classifier in the actually the classifier, not the matrix. And the way to look at it is, for example, to try to minimize the variance of the margin of the classifier that we obtained. And actually, it's a quite simple constraint optimization problem that one can solve analytically. And the optimal shot allocation is basically, well, we take some part of our whole budget and somehow weight the importance or the score of the specific entry, how important it is. And the importance is basically, well, some variance of the related to the binomial distribution, not that important, let's say, but the most important is that it's proportional in some way, let's say polynomially at least, to this dual coefficient, so exactly the importance of the point, right? So in general, this optimal allocation favors the points that have big alpha coefficients, or the actual value of alpha coefficients. So basically, support vectors. We are always looking for support vectors, and we try to get the best precision out of them. Of course, there are different approaches. We can, instead of minimizing the variance of the margin, we can minimize the variance of the decision function. That completely makes sense. But qualitatively, we get the same result. We always favor the kernel entries that have a huge importance in terms of alpha. Just to, let's say, remind you, the uniform allocation has no information about the structure of the classifier. We just equally distribute the whole budget into the each kernel entry, which when we have n data points, it's case like n minus 1 divided by 2. Okay, everything is very nice and theoretical, but there's one caveat. This assumes that we actually do have access, so-called oracle access, to the solution, the exact solution and the exact values of alpha. And well, it's not the case. As we will perform more measurements, we can start to decide where to allocate more points, but our estimates so far will be noisy. So we have to take into account that the whole thing here is an oracle-based allocation. So the ideal case, and it's defined on so-called active set, so the set of support vectors. But within the preliminary estimation of the structure, we can actually make mistake and identify some point which is not a support vector as a support vector, or vice versa. So we have to add this kind of an exploration term that takes into account the uncertainty of estimation of a point so far, and somehow favor also points that we haven't identified as support vectors, but they still have a non-zero probability of actually becoming a support vectors as we increase the precision of our measurements, or the vice versa, if we identified some points which are in the active set, but maybe when we increase the precision of our estimation, they will leave this set. And together, I propose some kind of a convex combination of those two effects, which I call sensitivity and instability term. This gives us scores, which then translate linearly to how many measurements we dedicate to each kernel entry. Okay, and that's the algorithm, basically. The first part is basically the uniform part, although in the uniform we would devote whole budget here. In the adaptive algorithm that I propose, we take some measurement budget and use uniform measurement as a pilot. So we use only a very small part of the budget that we have to just feel initially the structure in the data and then start adaptive rounds. So learn SVM, see the structure of the problem, assign measurements to points that we believe are important, use some part of the budget, learn what we've obtained, and proceed in the loop until we run out of the whole budget with which is started, or we reach a stopping criterion, which I will talk about in a moment. And the very first experiment I performed, results are given here. I will very quickly talk about it. So I used a pilot plus 5 adaptive rounds, and in the end there's a uniform, so the standard way how we do it, baseline. And this is a root mean square error for the kernel matrix estimation, and we see that uniform baseline is much better. Okay, but what does it mean? That actually means what we wanted to do. We don't want to uncover the whole kernel matrix as well as we can, but actually we, because uniform does it very well, but actually we would like to estimate as best as we can some sub part of this matrix, and that's exactly what is visible on the second plot. This is a again root mean square error for the sub matrix, which is spanned only by true support vectors. And if we look at it now, the story is completely different. After pilot round, of course we are worse because we just devoted a smaller budget, but the same algorithm was done. But as we already after the first round, we surpassed the uniform baseline and proceed of being better, with some kind of a saturation. So the story is the following. If we have a given budget and use this adaptive algorithm, we have much better estimation of points that actually matter. When we look of the Jacquard index, or how well we identify support vectors, so again, the points that actually matter, again, we beat quite fast the uniform baseline already, basically after the first round or the second round. If we also weight this support vectors recovery by the importance of those support vectors, actually the results, I guess, are even better. And well, remember, I just optimized for as small error in margin as I can. And well, as I optimize it, we see that uniform method is not optimized for that, and it performs worse, and adaptive beats much better. It beats it quite a lot. Okay, but that's what we optimized for, right? But let's see if it translates to also, for example, decision function. And again, yes, absolutely. So with adaptive scheme, we quite fast are much better with also with the, let's say, decision of the classifier, the recovery of the classifier as decision. Okay, so that's what's actually here is the exact experiment that I showed you before in the whole landscape of different experiments that we can perform. Actually, as I said, it was a very good first experiment because it's deep in the regime that I want to talk about. So let's say we have a fixed budget, the same experiment that we had before. Red color means that adaptive algorithm is better. Blue uniform approach is better. And so the question is adaptive always better? And actually not. It seems like it doesn't depend that much on the margin itself, but it does depend, as you can see, a line here between the uniform and adaptive dominance. It depends on the sparsity of these dual vectors. And what does it mean? In here, with Gini index 0, it's basically all points in our problem matter at the same level equally, okay? And this is, well, if you optimize in such a setup, uniform allocation is the optimal one, okay? And okay, that the second count will be in a moment. And as the structure in our problem is, as I would say, not visible very much, okay, so the distribution is in alphas is quite flat. Well, usually uniform is better, but for the for the problems that we actually care about, where there is some structure and SVM can provide some nice results, actually adaptive basically always win. The question is, why is it blue and not gray? Because I would guess that adaptive should, and this adaptive algorithm that I provide should reduce to the uniform allocation naturally in this regime. And it does, absolutely. But let's remember that it proceeds in some kind of experimental rounds that make decisions based on what they measured so far. And so far, let's say, means measurements were containing some noise. So there is a small fluctuation in the probabilistic fluctuation in the optimal strategy found by adaptive algorithm, and uniform is just more robust. It doesn't take into account any measurement noise well, until it actually ends. Well, at any point, basically, it doesn't take into account what we've measured so far. So uniform is a little bit more robust, but in the regime of experiments that I guess do not matter for our use cases. And okay, so I basically said, well, we have some fixed budget, we have some money to spend on quantum computer, then we could use adaptive algorithm. But let's invert the question. Okay, maybe we don't have a fixed budget, or we know what's the ceiling, but we want to spend as little measurements as we can. And that's exactly a moment when we can introduce an early stopping threshold. So let's say that we find some internal characteristic of the algorithm that will be that will somehow indicate that our algorithm stabilized. And actually, I'm not providing here on the slide, but the difference between dual coefficients between rounds work perfectly for that. And if we introduce some kind of a threshold to decide whether dual coefficient estimation doesn't change that much, then, well, we can introduce some early stopping. And I guess it's better to start with the lower plot for this experiment that I'm showing. So we have on the x-axis, both here and here, this threshold. And if it's very small, this threshold, it means that we are running the algorithm until the dual coefficients stabilize very much with very good resolution. And let's say up to a point, and we are plotting here a relative shortcut. We have some short budget, and we ask how much of the budget we use. And basically, up to this point, after this threshold, the algorithm uses all budget that we have available. Well, because the threshold is too small. But as we start to increase this threshold, we can see that the algorithm starts to stop earlier and earlier. And let's say at a threshold of 10 to minus 2, actually we use only 50% of the shots. Okay, but now let's compare it to the performance of the classifier retrieval that we get, and that's exactly the upper plot. Again, red means adaptive retrieval is better, blue uniform is better. And what we can see that for the most of those thresholds, adaptive wins, and here is the crossing point when we can say adaptive and uniform are on par. Okay, so they have the same, on average, the same score. And when we look at what's the value of the threshold, it's around 1/2. But the most important thing is it's exactly at 60% of the budget. So 16% of the budget. So it means that we can get, with adaptive scheme, we can get the same behavior as in uniform, but using only 16% or less than 20% of the resources that are needed for uniform. So it's a huge saving in resources. Okay, I think I'll be finishing slowly. So one more thing. So far, those experiments were done in a very synthetic manner, synthetic data sets. And actually, I was estimating the kernel that I knew very well, and actually it was a classical kernel. Well, the model was the same as for Quantum, but I used just RBF kernel. But actually, from one of the previous papers I wrote, I have access to some quantum kernels already estimated or actually calculated with a state vector simulation that I can put to use. They were obtained with a very specific circuit. And I would like to show for a very specific task also. As I'm working in Earth observation, we had a hyperspectral data set that, we had hundreds of features, and the task was to estimate, this is actually ground truth of an image, and those things here are crops, different crops that grow on the field, okay? And this is a ground truth, okay? And the classifier in the end performed quite well, actually, when we compared even to classical state-of-the-art methods in the crop classification, with some, of course, misclassifications. But that's not the most important thing. The most important thing is that actually I have those kernels estimated for a wide range of qubits, so also the number of features that we used. And it's between, n is not the data set size, but number of features that we take. And between, I think, 2 to 100. And if you know something about quantum machine learning, you probably know something about Barren plateaus or kernel concentration. And basically what we see always is that as we increase the size of the computer that we use, quantum device that we use, the points become less and less distinguishable from each other. That's here indicated by the standard deviation of the kernel entry. Okay, and that's what we see. Now points are the standard deviation is quite big, and now it's order of 10 to minus 3. Okay, there are actually 4 faults, so 4 kernels, and there's a mean here. And the metric that we use again, and that we've also used here actually, is the difference of the root mean square error of the decision function and difference between the uniform and adaptive. And positive value is adaptive is better, negative value uniform is better. So at the small problem sizes, well, uniform is actually, I guess, maybe not with a statistical significance, but it's better. But as we increase the problem size, we see that we are in the regime of positive values, so adaptive is better, and it makes sense. Well, we are using the same actually budget here, but we are placing our measurements smartly, and that's quite an important statement here, that we know that we have huge problem with barren plateaus, with kernel concentration, and with adaptive scheme, I would say that we can, within the same budget, look a little bit deeper into the regime of barren plateaus. Okay, so that's extremely useful in my opinion. And well, at some point, of course, within the budget, well, you cannot do anything, and it's basically random which method is better, because both of them fail. The second plot is also very informative, I guess. The same metric, so adaptive versus uniform, and the budget that we use. Okay, and within the small budget, it doesn't matter, because we don't have enough shots. But this is a very small budget, as you can see. It's a budget per shot, per kernel entry. Well, basically, we don't have enough shots to uncover meaningful structure, so it basically works almost like a uniform. But if we increase our budget, we start to see that adaptive makes much better use of the budget that we currently have. It's for qubit number 50. Okay, so moderate size, this size problem. And of course, if the budget is extremely, unreasonably big, actually it doesn't matter if we use uniform or adaptive scheme, because, we basically recover ideally the classifier. But in the end, I guess that what really matters is the reasonable shot budget, and within this, adaptive algorithm is just much better. So I would like to finish. So as I said, within the adaptive allocation algorithm, we can either use same budget and almost always get a better classifier reconstruction, or smaller budget, but then at the same quality of the classifier reconstruction. It can, okay, so the whole idea was that within the theory, I haven't assumed that we're using quantum kernels. So if we have any other approach to measurement-based kernels, repetition here, then actually the whole algorithm will also apply if this is with binomial noise, but it's easily generalizable. And it's, not naturally aligned with quantum kernels. For future directions, I will start with the second thing. Well, I think it would be nice. I don't know if anybody except the quantum kernels kernel community use some kind of a kernel estimation, right? But if you know about some community that uses these measurement-based kernels, then I guess the algorithm can be extended also to this domain. The first point, very near future. Okay, so I want to provide some impact with this research, not just a paper. So I actually wrote a whole Python package that I wanted to release it by today, but it's a little bit too early. I have to run some tests. But basically, the idea is that if you want to use quantum kernels, quantum support vector machines, you can use Qiskit, PennyLane, any kind of framework. But the package that I'll provide just seamlessly, you can just import it and use it to do all the work for you within the measurement allocation. So it will be really easy to use adaptive measurement scheme that you don't have to think about, but you get much better results. So, well, you're welcome to use it as soon as it's released, I guess, in the next month. One more thing is, so far, well, it's kind of proof of concept. So it uses synthetic, so simulator approach that I've implemented, and it also connects to IBM device API. So you can also use actual quantum devices, quantum computers that are provided by IBM, and their backends. Okay, so I think hopefully it will be useful. Yeah, and well, this was just focused on SVMs, but I guess in many different routines, and I'm actually working on that, one can extend those results to not only to SVMs, but I know kernel-rich regression or Gaussian processes. So that's not the last word here, but if you want to have a look at the paper, much more details there, this is it. And for the last seconds, I would like to mention one thing, a story that every researcher is scared of. So I thought this is a kind of, nobody thought about this idea, but it's reasonable. Maybe because actually we do not think really seriously about actually running quantum machine learning devices on the actual routines on actual devices. Maybe it's a little bit early. So I thought that, well, I have an excellent idea, I will work on it. And well, as soon as actually the first version of the paper was ready, but not yet submitted, another group submitted very similar paper. It's different, but very similar paper, the same idea. So I would like to advertise them also. I think there was a 1 week difference between those two papers. They were first, okay, and they have, well, I guess it's a complementary work, and actually we started working together since then. Okay, so I guess thank you very much for your attention. Okay. One more thing, I'm Artur Miroszewski. You can see my email, and if you would like to start collaboration with me within Philab, so maybe quantum machine learning applied to Earth observation, if you're interested, well, we should get in touch. And one announcement: next year. Actually, end of this year, we'll start a challenge on quantum machine learning, and I would love to see many submissions there. So think about it, and maybe add me on LinkedIn or anywhere, so you will know when we start it. Thank you very much.
Thanks, Artur. Okay, we are overdue, but I see there's one question on the chat that was at the very beginning of the talk. Once encoded in quantum states, can we use the classical machine learning models to, like regression on SVM, to train, or we need some modification there too?
In many cases, well, exactly within the quantum machine learning approaches for the near-term quantum computing is basically that in many cases we actually use classical routines, the standard ones, but we use quantum device only to do a very small calculation that we believe is a little bit faster on the quantum machine. So absolutely yes.
Okay.
In most cases, that's actually what we do. Okay, so we delegate a very small problem within the whole routine to a quantum computer, and the rest is basically the standard classical routine.
Okay, all right. Okay, thanks Artur once again, and let's go to the next talk. Jakub Cybulski
Thank you.
will give a talk about paradoxes of high-dimensional quantum models. Jakub, if you are ready,
let me
this one is yours.
just get my desktop.
Okay.
Okay. So I'm Jakub Cybulski from Enquantum Australia. I'm also holding an honorary associate professorship in the School of IT at Deakin University. And today I'm going to talk about paradoxes in high-dimensional quantum models. Before I start, this is my website, jakubcybulski.com. If you want the presentation, you go to my website, click presentations, and at the moment, the very top, presentation has a PDF attached to it, so you could grab it. Let's get into slides. So I'm going to walk you through some issues with high-dimensional quantum models and why this talk. Everybody talks about getting a quantum machine with lots of qubits and having lots of parameters, and everybody thinks that the problems will be solved at that point in time. And this talk is to show some difficulties we're going to face once we start climbing into those high-dimensional quantum spaces, more qubits, more dimensions in a Hilbert space. And I'm first going to walk you through pure geometry, basically take you through the naive model of what's happening in high-dimensional quantum space, and then we're going to look at what happens in the actual quantum model. I'm going to use not very highly dimensional model. It's a very simple penny lane program. It has only 2 qubits, but it will illustrate some of the issues that we are facing. You can see here that it's not an ordinary model. It looks very ordinary, but if you look at the code, you can see that I included some nonlinearity in rotational games in a phase. And also I used mixed observable at the end just to make our life more difficult. So to illustrate what is the shape of this model in Hilbert space. The most important thing is that when this is executing, of course, execution is not happening in classical domain, but it's in Hilbert space. And basically, the execution leaves the trail of states that this model is walking through. Each operation is slightly altering the state, and eventually it arrives at the final state when we do the measurement. I'm not going to explain what's happening here, but I just want to show you that, or mention that, yes, execution leaves a trail of states. And when we parameterize this model, the parameters, whether they're inputs and trainable parameters, they alter the path through the Hilbert space. And if you were to look at all possible trails with different parameterizations, what emerges is some kind of a shape. And this is the geometry of what this model is capable of generating in Hilbert space. And it's a smooth curved surface, which we called the manifold. And I'll show you some examples of those manifolds in a minute. What's happening when you try to optimize such a parameterized quantum model? Of course, the key is the circuit. The circuit will have some state initialization, and then the ansatz, which is parameterized. And we have the weights and the input parameters, which are accessible to the optimizer. Usually there's some gradients attached to the weight parameters, so that if it's a gradient-based optimizer, can use those gradients to find the best path through the parameter space. The state evolution is completely invisible to the optimizer. It can only see what comes out of measurements and what can put inside. What's important for the optimizer is that it's driven by the cost landscape, which is the effect of applying the cost function to results produced against results expected. And it is a scalar field that has its own shape, and the optimizer is looking for the lower minimum value of the cost associated with this model. The optimizer is completely oblivious to what's happening inside the circuit. It doesn't know that the parameters are attached to the operations, that operations live on qubits, that the qubits are entangled, And because of that, the optimizer is trying to modify some of the parameter values. We have non-local interactions between operations and the parameters. And classical optimizer really has no clue what's happening there. On the right-hand side, you can see two different optimizers running through the parameter space. Actually, the initial point of the optimization is on the right-hand side. This parameter 1, parameter 2. And as we optimize the parameters, one red is the classical optimizer. It's a gradient descent optimizer. It goes through the smooth space and ends somewhere here. If you take the quantum natural gradient optimizer, which is aware of the fact that we are moving through the Hilbert space, it takes some shortcuts, and it actually produces much better final result of this optimization. And why is that so? It will be evident in this talk. But we're going to talk about the classical optimization and quantum natural gradient optimization, which is aware of the quantum space that this optimization really is modifying. So this is just to visualize the two different realms, the two different spaces that take execution of the circuit and its optimization is actually hinges upon. The first, the top, is the cost landscape, which is completely living in the classical parameter space. This is what the optimizer can see. And this landscape is the product of creating the classical surface over of the parameters. For each parameter combination, we have a cost, and that cost, the dot on the space, it represents the model which generated that cost. And the classical optimizer, of course, if it's a gradient-based optimizer, will slide down towards the lowest cost in the space, and hopefully it's the solution that you want. Now, for each model which is created here and the model is executing, the execution is taking place in the Hilbert space. And the Hilbert space, we all know it's big, it's very big, it's exponentially large, considering number of qubits. But this is not what I would like to talk about in here. I want to talk about the shape of this space, and I want to talk about what's happening there. And a lot of things that happen is completely counterintuitive. This is actually worth knowing that a phenomena of Hilbert space, high-dimensional Hilbert space, is not what we expect. I mentioned a few issues with what's happening here. One of the issues is that the circuit has entanglements, and those CNOT gates, they fold and manipulate the shape in the Hilbert space. This shape is warped. It's warped because of the metric that we use in the Hilbert space. And I'll talk about the metric later on. It's a Fubini study metric, which basically folds the manifold on which the model lives. You can see those little worms around here. They are actually optimization paths taken through the Hilbert space while the optimization happens in the process of classical optimization. And you can see that they curve in a completely unnatural way because they follow the surface, the surface in the Hilbert space. But let's start with something much simpler. Okay, so imagine that we have n-dimensional ball. The two-dimensional ball is a section on the line. Sorry, this is two-dimensional ball, one-dimensional ball section on the line. Two-dimensional ball is a circle. Three-dimensional ball is a sphere. And n-dimensional balls is you add dimensions to it, and it has the same radius, every single time. And It's interesting because we could calculate the volume of this n-dimensional ball. And here is the formula for the volume. It boils down to the circuit, the surface of the circle and the volume of the sphere. And the intuition tells us that if we start adding dimensions to the ball, the volume will grow. We add dimensions and there's more space. What's counterintuitive is that it grows only up to the dimensions of 5. It's actually 5.25. And after that, the volume of that n-dimensional ball starts shrinking to 0. Okay, so in high dimensional space, there is no space inside that ball. If we were to put the cost landscape inside this n-dimensional ball, the cost landscape would have the minimum closest to the center of this sphere, and some initial point would be somewhere away, and we could follow the path down towards the optimum. Well, that's great. Now, what happens once we start growing dimensions? The volume shrinks, and surprisingly, it doesn't shrink uniformly. Its shape is very similar to the funnel. So at the surface, it's like the top of the funnel. There's a lot of space in there. And in the center, there's less and less space. So basically, the volume concentrates around the outer surface of the sphere. So this is where all this volume is. Inside, there is more and more sparse space. So we were going to draw the cost landscape inside this n-dimensional, like here, 45-dimensional space. So we're going to find out that there is not enough space to unfold it, and therefore it flattens. The whole space flattens. That's what's called barren plateau, basically. It's a pure geometry which drives the emergence of barren plateaus in multidimensional, high-dimensional quantum models. So basically, the gradient starts disappearing because there's not enough space, and all the space is concentrated near the surface. Here's just calculations. I calculate here the 1% volume away from the crust of the sphere. So in 3-dimensional, that 1% of the outer, the 1% shell of the outer sphere, it roughly contains 3% of the total volume. In 45 dimensions, it's about 36% of the volume. In 500 dimensions, it's over 99% of the volume. So 1% of shell away from the crust, virtually all volume of this ball is contained in there. How big is 500 dimensions? It's basically 9 qubits. 9 qubits is 512 dimensions in space. So it's very, very easy to actually get to this cataclysmic shrinkage of volume in n-dimensional space. We're talking about having models which run on 100 qubits or 1,000 qubits in the future. I don't know how much, is almost zero volume fits inside this ball. There's more weird things that are happening there. If we start calculating the point-to-point distance, now here we talk about Euclidean distance. So we have here multidimensional ball, and the question is, how far is from one point to another point, from the initial point to the target point? If we started looking at the distribution of point-to-point distances in multi-dimensions, we find that initially there is a large variety of different distances. And with dimensions, suddenly we find that the distances concentrate around the mean. There's actually less and less variety inside that ball. So if we stand on the surface of your landscape, the cost landscape, and you're looking around at which way to move down. First, you don't see down because it's flat. Secondly, you can't see distances because the distance between any 2 points is the same, including the distance from the point you're standing in and the target. The other unusual thing that's happening is that the angular distance between 2 points, it starts approaching orthogonal. That means every 2 points in this multidimensional sphere are orthogonal to each other. So this is completely weird because you have no direction, you have no distances, and everywhere you look at is you're completely lost. There is no way to navigate towards the target. What's worse is that if you initialize your model randomly, that means it's quite likely you're going to initialize it quite far from the optimum. There's no way you could actually get from the point you're standing in to the target. So in such a case, you either need to change the metric or you need to change the point you initialize the model with. Another interesting thing that's happening is in this particular metaphor for the Hilbert space, we also have a problems with entropy. The entropy in this particular case, because the volume is a geometric entropy, it's it's ensemble entropy we're talking about here. Virtually all possible states are concentrated in that crust, very narrow crust. We have the greatest variety of different states in this very narrow space, which means that if you're standing anywhere, you're surrounded by states which are similar and vastly different to what you want to look for. So there is no similarity between the optimum and the state you're in. By the way, you can see there's a lot of text here. It's written for your convenience. I'm talking about the picture, and you could take it away and walk through it and read it in great detail. And there's another weird thing that's happening in this multidimensional space. And this is sparsity of measurement. If we start with few qubits and you measure them all, let's say 1,000 times, you can see that the space for the distribution of different shots attached to the outcomes is quite clear, and we could measure it with quite precision. If we maintain the same number of shots, but start measuring more qubits, each extra qubit, it doubles number of outcomes. If we move from 2 qubits to 5 qubits, the number of shots distributed in the measurement of this circuit is insufficient to get any picture of the distribution. You have highly imprecise outcome. So with 5 dimensions, you need to start thinking not in terms of different types of outcomes, but in terms of precision that you want to get into. Okay, we talked about something completely abstract. It's a pure geometry. So far, I didn't talk about quantum models at all. I talked about n-dimensional balls. The curious thing is that the rules, the geometry governing the Hilbert space is not much different from the n-ball. Virtually all paradoxical phenomena that I talked about, they happen in both, but slightly different. So all states in n-dimensional ball are concentrated in narrow shell near the surface. The space is flat and distance measures between states are Euclidean. That's not true for the quantum space. Initial and target state are in this shell. The vectors between pairs of states are near orthogonal, and entropy represents spatial probability, high entropy near the surface. What's happening in high-dimensional quantum space? All states are represented within a very complex multidimensional projective manifold in Hilbert space. It is asymmetric. It looks like a maze. It looks like a starfish. Why a starfish? Why is it not symmetric? Basically, it's to do with the constraint that probability of alternative states must equal 1. So if you look at moving in every dimension, it's like an elastic band. You move in one dimension, you want to get more space in that way, then probabilities have to add to 1, so it has to shrink from other dimensions. That's why we have this star spiky shape, because of that. The manifold is measured using Fubini study metric, which is the quantum fidelity metric, measures the overlap between two states, and is derived from polar coordinates. The interior of the manifold, this is the star, it's a full rank mixed states. That means all eigenvalues are greater than 0. The outer boundary, just on the outside of it, the states start losing the rank, and at least one of the eigenvalues is 0. The pure states are within the outer boundary, but they have only one eigenvalue equal to 0, and pure states represent just extreme points in the outer boundary. If you look at this as an idealized, simplified version of, which is not starfish, it's not spiky, but it's a surface of the outer boundary of the n-dimensional manifold, then if you look from the perspective of the target state, the same phenomena is going to happen as in n-ball. That means all other states will be near orthogonal to it. So what it means is that virtually all other states, pure states, which exist in this manifold, are in the narrow band on the equatorial band around the surface. So if you start looking for the path from the initial state to the target state, it's quite difficult because all states in between are around the equator, but you need to get to the North Pole. So that's difficult. You need to have some new way of optimizing such models, which actually could bypass those problems. So what the state looks like. So I prepared a bit of a simulation for you. Basically, we are going to look at a very similar model that you're familiar with, the Bloch sphere. But we're going to look at the generalized Bloch sphere. And unlike what happens with a single qubit Bloch sphere, the generalized Bloch body is a true representation of what the states look like in n-dimensional Hilbert space. So let me get to my example. So this is the actual projection of that little program I showed you initially. This is what the outer surface looks like in this space. Now, this is the projection into the observable dimensions. What is this observable dimension? The manifold that we're looking at, it's only on 2 qubits, but we construct the projective space from every single possible measurement that we could take, the ansatz. And every single possible measurement, looking at Pauli's operators, there's about 15 combinations of 4 different Pauli combinations in this space. So we're talking about 15-dimensional manifold that we're looking at, and we're looking only through the perspective of 3 selective observables, which were actually observables linked to that particular model. Okay, you can see it's highly crumpled, and it's quite difficult to see what's happening there. And those are the 4 possible traces, possible optimization paths through this manifold. You can see that at the bottom, it's the lowest cost. And because the cost is calculated based on the observables, so you could imagine that this should be somewhere at the bottom. Okay, and that's what happens here. It's pretty good. However, looking through the observables, we are prioritizing certain dimensions, certain coordinates in this multidimensional space, 15-dimensional space. And we are really interested in what the ansatz looks like, rather than what we can see through the observables. So if you want to see the full picture of the ansatz, This is still the same what we saw here. Before I got into this, I should probably explain. This is the projection onto your observables. This is the true shape of this 15-dimensional space. And this is the nice and smooth cost landscape. This is what the optimizer can see. The optimizer thinks it's a nice and smooth path down, but the actual evolution of the state is actually over this crumpled geometry. Now, I mentioned that I should be looking at the ansatz itself. Okay, I showed you before two different paths through the optimization path of the little program. And those paths are highlighted here. Now, you can see that this is the classical optimizer. This is the quantum natural gradient optimizer. The classical optimizer is following the cost landscape. It's following the cost landscape, and it's actually walking on the surface and the edges of this multidimensional tetrahedron. Okay, so what does it mean that it's walking there? Because of the Fubini study metric, the measurement used in quantum space, at the edge of those crumpled space, the dimensions change, and the metric changes in such a way that the closer you get to the edge, the further is the space to the edge. And so the classical optimizer is walking through the almost infinite space between those two different surfaces. Very inefficient way of moving towards the optimum. Now, what happens with the quantum natural gradient? It follows the edges of this space. It actually understands what is the shortest path in this n-dimensional space. And the edges are the shortest path. It just looks like it's a longer way because of the projection. So coming back to our Hilbert space, I just show you here. I try to explain. I don't have time for more explanation. It's a fascinating area. The conclusion basically here is that the classical optimizers basically blindly walk through the artificial cost landscape. The key here is to be able to do anything with multidimensional Hilbert space, you really need to pick a good cost landscape. That means you need to pick a good cost. Okay, that's very, very difficult. So we use straight vanilla cost functions, and we happily apply them to quantum models. That's not the way to do it. The second thing is that we actually have alternatives to using classical optimization methods. We have quantum natural gradient method. It actually understands that it actually takes the circuit, it derives the geometry of the circuit from its operations, and then builds the quantum Fisher information matrix at each step, and understands what is the geometry, the best geometry to walk through, rather than using the cost landscape. It's calculated the cost the same way so that it knows what is the true cost, but it finds the best path through the geometry of the highly dimensional quantum space. So that takes us to the end. What I wanted to tell you is that bizarre things are happening in Hilbert space. Bizarre things are happening in projective Hilbert space. And this is actually what we use in quantum machine learning. We actually have different ways of measuring distances in the space. We have unusual things happening, like the volume concentrates on the outside of the model. The manifold is a multidimensional manifold. Entropy works differently. The entropy in Hilbert space is actually in the center of this shape of this geometry. And it's actually a fascinating area for all of us to understand, because a lot of us, we work with quantum models as if they were black boxes with parameters, and they're not. Okay. I work with Sebastian Zions one of my colleagues on this area, especially that we look at alternative quantum information field theory. So that the theory which explains what happens in multidimensional spaces, in parameter spaces, classical versus the quantum representation of it. And if you have any questions, you're welcome to ask. Thank you.
Okay, great. Thanks, Jacob. Do we have some questions to Jacob? I do not see questions on the chat now. And as we are overdue, I propose to move forward to the next talk. But
Okay.
Jacob, if you can stay with us, because there can be some questions later on the chat, and you can try to answer. But for now, let's try to move to the next talk. That the speaker is Sebastian Dziura this time. So Sebastian is with us. Thank you, Jacob, again. Thanks. And Sebastian, if you're ready, the Zoom is yours. Thanks.
Can you hear me?
Yes, I can hear you and I can see your slides.
Okay, great. So hello, everyone. My name is Sebastian Dziura. I am PhD student at Center of Excellence in Artificial Intelligence at IGH University of Kraków. And today I will talk to you about our recent research that we've done with Tomasz Botycki and Piotr Gawron about auto-quantum machine learning for multi-source classification. Okay, so starting from introduction to the topic, what we treat as multi-source data. It's information about a single observed object collected from multiple complementary sources. So the multi-source data set includes like different data origins. For example, when two cameras observe one object from different places, from different angles. The data sets with multiple modalities, when we have image and time series or tabular data. And also different timings. For example, when we have satellite photos of the same city, but taken from in different times. Okay, so when we have this multi-source data set, now we want to integrate it somehow. And this field is multi-source information fusion, which is a process to aggregate and transform multi-source data into useful information to obtain richer and more accurate decision outcomes. And here we can distinguish three levels of fusion. First one is data level fusion, also called early fusion. It's when we integrate the data, the raw data straight from the sensors. So before any processing. So it retains the maximal amount of information, which is a plus, but it has also limits because it's sensitive to noise and requires homogeneous sensors and perfect alignment so that we can integrate them. A bit more flexible is feature level fusion, which is also called mid-fusion. This level of fusion is when we integrate data that is information that are already started to be processed, but still before the decision, like in our case, classification. We can apply it to. We have more freedom to apply it than the data level fusion, because we can also apply it to multimodal data, and so it can capture these cross-modality correlations in the features. And we have also decision level fusion. It's the most robust one of these. We make a decision on each source separately. So for each data from each source, we have a separate pipeline up to the decision. In our example, classification. So we make a classification based on data from each source separately, so we can have completely different algorithm. But at the end, to make a final decision, we take all the decisions, and usually we put some weights on them, and in some way we make a final decision. So out of this, we wanted to focus on one. So we chose the feature level fusion as it's a good compromise between all these three levels. And how we want to do it with quantum machine learning. Already, Paweł Góra already made a nice introduction to the topic, so I'll just go briefly. So we have classical data, and then we want to encode it to a quantum computer with some unitary operation. Then in the yellow box, we have parameterized quantum circuits, so the ansatz already mentioned earlier, usually built from some single qubit gates with rotations that are where the angle of the rotation is the parameter that we can train in our training loop, and some multi-qubit gates that make the interactions between qubits. And at the end, we need measurement to get our data back to classical, and so that we can apply loss functions and optimize our parameters. Okay, but I showing you this because now I want to show you how big variety we have in data encoding and parameterized quantum circuits. So from which we can choose. So first, quantum encoding, which is called quantum embedding, is a presentation method where classical data is mapped into quantum state or a quantum feature space, enabling processing via quantum circuits. And a few examples already also mentioned. Basis encoding, when we on qubits we put bits, so we can encode binary data. We have angle embedding, when on each qubit we apply one feature by rotating the qubit by then angle defined by the input classical data we have. So on n qubits we can n features, and amplitude embedding, where on n qubits we can apply 2 to the power of n features because of applying each feature into the probability amplitude of any state we have in our superposition of our quantum system. And of course, there are many more methods. These are just 3 basic ones. Also, in the ansatz, we have many possibilities. I will not go into details, but these are just pictures from PennyLane that some of the possible types of variational layers we have already in the PennyLane package. So we have a big variety of architectures we can make for our quantum machine learning, for our variational circuits. That's why we wanted to see if we can apply some quantum architecture search. So in our experiments, we used Accumulator, which is a quantum architecture search software built by Tomasz Botycki. And we wanted to see if it can find better models, if it will work well for our problem of multi-source classifications algorithms. So we have a model trained, then Accumulator gets the metrics, and then it gives us another architecture, and it works a bit like hyperparameter optimization, but instead of hyperparameters, we have different architectures. It's built on Optuna, so this comparison is quite accurate. Okay, so it's search for these architectures in a given search space that we give it, and we wanted to see how it works, and so let's go to some experiments we performed. First one, we used some synthetic data set, so we just took the MNIST, divided in half. We took 6 digits, and we limited to 3 digits our data set, and each image we split in half. Reduce some dimensionality, And these were our, let's say, simulation synthetic multi-source data sets, treated like one half of one source and second half as another source. And we used as a baseline for classical baseline for our experiments, we took some just simple multi-layer perceptron, and here in the yellow box we treated both sources separately. To later here in the blue box, we concatenated them to process them later together. So here the fusion happens. At the end, we have a classification. And for the quantum part, we just replaced the blue part. The yellow part feature extractors are kept the same classical ones, and here we replaced with the quantum. So our accumulator was just looking for the blue part and giving us new architectures. And here in the green, we have also checked two options with optional linear layer, classical one, to use more quantum states from our measurement. And okay, let's go to the results. Of course, still classical MLP worked the best in our case, but we can see that it used much more trainable parameters. And here we have the results for manually found circuit. We see that it wasn't as good as the one found by accumulator, both with and without this linear, classical linear output layer. Of course, if we were looking, we searched manually through the whole search space given to accumulator, we would find finally those, but we can see that it was much more convenient to use accumulator to find a good architectures, and it can help us with in the research. And it found actually quite good, even comparable to this classical MLP. And so if we worked on a synthetic data set, we wanted to check it also on a real data set. So we applied it to the change detection task based on ONERA dataset. So given a pair of corresponding multispectral images depicting the same region and take at different times, find the regions that differ between pictures. So here on visualization, we have RGB photos, but we used, of course, multispectral ones. And we want to find on each pixel if there was some change between those pictures, the change that we are looking for. Yes, so we use quite similar architectures, baseline and the quantum one. Just fusion happens already in this feature extractor in this classical part. So here we see we have quite similar, and here we also tried with two different classical MLPs, because first we see that classical MLP, of course, was again better comparing to the found by accumulator, but still, let's say, wasn't much worse. But we saw that it's also a number of parameters. I know it's not perfect for comparison between classical and quantum, but it gives us some intuition at least. And so we wanted to check also how smaller MLP will work with comparable number of trainable parameters, and our quantum models worked actually even better. It could even beat the classical MLP. And what is interesting that the best models found here with quantum models were actually the ones with the smallest number of these parameters. So very simple, basic models, architectures, which is also very interesting. Okay, so we used PennyLane as actually previous speakers to implement the quantum architectures, but and we used PyTorch for which is quite well works with PennyLane for a whole hybrid architecture. And going to conclusions, even the basic automated quantum machine learning consistently outperforms manually selected architectures. While quantum models did not surpass the best classical benchmarks, they achieved comparable accuracy levels. The quantum models reached competitive performance using significantly fewer trainable parameters than their classical counterparts. What is most important for us is that we see that we wanted to see if we can, in the further research, we can apply, we can use accumulator to instead of manually looking for architectures, and this is what we confirmed. If you will be interested, I can share with you links to the papers about accumulator and this one, and to the code of accumulator. That would be this. Just one more thing about our next steps. We want to work on because all this was, of course, on simulators, but we want to move to real quantum computers on Wilk quantum computer in Ostrava. It's quite new, and we should have access very soon. It's a computer from IQM in 24 qubits in star topology, which means that we have all-to-all qubits connectivity because by central resonator to connect all qubits. And here is a photo of this computer, and that would be this, a bit shorter than I planned. Thank you for your attention.
All right, thank you. Thanks. Do you have questions, Sebastian? Actually, I see that there is one question to Jacob on the chat. So Jacob, if you are still with us, you can try to answer on the chat, but maybe there are some questions to Sebastian. I don't see more questions now, but Sebastian, if you can stay with us until the end, then
sure.
Perhaps there will be some questions on the chat, but anyway, as we are overdue, we can go to our next and last talk for today. Karol Bartkiewicz is our next speaker. I hope that, yes, Karol is with us. Hi, Karol.
Hi.
So if you are ready, the Zoom is yours and we can start.
Okay. Let me just open the presentation.
Okay, good. That's fine.
Okay, so thank you for this. Is I think my second presentation during on this conference series, and this time I'll be talking about something different. So
good.
Yes, I'm ready to share my screen. Okay. Okay, window. Okay, can I? Okay, I will share my screen because it's. I think it's easier to do this with my screen. Okay, so this is my presentation. I would prefer showing it in some other layout, but I'm kind of lost with using this. I mean, view. It should be some presentation view. Yes, this is. Okay, so I'll be talking about some other paradigm to quantum computing that we are all familiar with. So this will be kind of basic in comparison to more advanced approaches, but I think it's very important to speak about it because, well, from my perspective, we should try to explore every avenue before starting to thinking seriously about quantum computing and its usability. So I'm interested more in basic research, and I'm a physicist. So together with Patricia Tulewicz, I think she's attending this conference from the start, and Professor Adam Miranowicz, we've been working on this notion of quantum counterparts of very basic electronic units or elements that we usually use for signal processing. Okay, so usually we forget when we think about resistors, capacitors, and inductors about the fourth element that is necessary if you think about the complementary of all the elements. It is the memory store. Okay, so it binds. It has some very interesting properties, and what I'm going to do in this short talk, I will show you how to go through this idea of memory store to quantum version of memory store, and show you how it relates to quantum computing in this reservoir computing framework, quantum reservoir computing framework. Okay, and I will show you how you can even observe some potential improvements over classical counterparts. So this is strongly related to the quantum version of Hopfield networks and pattern associative memory and pattern recovery. So the only problem is that we don't have memories for quantum systems, but it's I will show you how to bypass this by using something that we already even built in a lab some time ago, but we have to push this technology much further to make this theoretical idea that I'll be presenting feasible. Okay, so the memory needs irreversibility. So something must change in our usual paradigm for quantum computing to have this irreversibility. And quantum mechanics is reversible, and measurements destroys the state. Okay, so we don't want to have measurements. We want to keep this assumption that we need irreversibility. And we allow some gentle measurements, perhaps, but only to monitor what's going on inside the system that we're talking about, or maybe at the end of the output of the system. But essentially, the whole evolution that I'll be talking about is error-free, except one slide. Okay, so what is a memory store? So memory store is a register with memory. And this is the fourth element that was proposed some time ago. Now it's omnipresent. It's very popular in electronics. And there are some characteristics of it. So one of the characteristics is that it's responsible, let's say, to input current or output voltage at the memory store, actually forms this kind of hysteresis that you would know probably from magnetism, but with one very important difference. This hysteresis is pinched hysteresis, so this means that it has exactly zero at the center. Okay. So, and there are more important characteristics here. So another one is that actually we have frequency dependence. So depending on how you sweep the input current, your shape of the hysteresis will change. So we care about this because this is like a natural synapse for building something like neuromorphic computers and something that is in memory computing. Okay, so if we don't want to have like separate memory modules, perhaps it's better to think about using this kind of paradigm. Okay, so can we make something that is genuinely quantum and to recreate this behavior? So it is possible, but you have to realize from the start that, well, you are going to cheat, okay? Because your classical memory that recreates this kind of hysteresis has this memory parameter that is described by stochastic differential equation, and you have to use only unitary operations, okay? So how to do this? So, so the usual approach in literature is that you have a photon in, it undergoes some operation that rotates its polarization, and if it's let's say detected, or the output photon, then this N operation is applied, and well, and so this photon, and it's it's stored to this classical memory. Okay, so you just update essentially by some differential scheme this theta parameter, and you change the setting of your polarization sensitive device here. Okay, so there is this let's say classical memory or measurement device, but actually this is the way that you usually cheat if you want to build something that you would call a quantum memory store. Okay, and there's this gamma parameter that tells you how fast this so forget the previous history of measurements. Okay, and this is how you do this typically. And if you just feed photons over and over again after you will reach some equilibrium, so your memory doesn't get let's say updated. You will still store some pattern. You will reach some equilibrium. Okay, and in this case, your input drive will actually recover this kind of pattern. And you can say this is frozen memory. This is a single photon level. So this is something that people tried to do, but they didn't reach this pinched hysteresis for I don't know why, but this is one of the characteristic shapes that you should see. Okay, so two distinct up-down branches, memory, and it should collapse to a line at high frequency. So we need to investigate it. Okay, and there are other signatures. So and the device is programmable, and we have like 3 knobs. So theta 0, so initial state of the memory parameter, gamma, so this is the forgetting rate, and this eta parameter, which is like this amplification parameter. Okay, so what you actually will see in reality is that if your drive or your, let's say, input polarization, which show like that, this is like linear polarization, is like rotated, your response to this in this device. So one notice here that this we have to do adiabatically. So this means that we wait for several steps for this to stabilize, and then we actually change something in the system in reality, because if we don't do that, we deal with exactly the situation that we have here. So if we, in the limit of like extremely fast, let's say, updates to the memory, you will see that this system will for some time evolve in so-called transient regime, and at the end it will stabilize to reach this settled area. So this is the final pattern that is stored. Okay, so drive and output, this is what you will actually see here. Okay, so this could signify the amount of photons polarized, let's say, vertically, and the bottom horizontally, and your input and output relation is actually here. So this is what is forming this hysteresis that you will see. Okay, so there is some lag, and this is to be expected, because well, this is just a dynamical system that has to go to some attractor. So this means that it's out of equilibrium and then it reaches equilibrium. And the way it actually reaches the equilibrium, you just feed more photons. Okay, so so the first photon that goes through, well, it won't be so good. The other one will be better, and the other one better, and you still just keep feeding the same input all the time. And finally, it stabilizes at the pattern that you want to observe. Okay, so this is what you do. And if you change the frequency of your drive, you will see that this hysteresis shape will change. And there's just to show you what are the possible patterns. There's this ratio of this sweep frequency and gamma parameter. So this the rate at which the system forgets. And each pattern is like a let's say can be interpreted as a way as information that is being stored in this device. okay, in this large adiabatic time, let's say, scale. And what is also interesting is that this area enclosed by this loop also has some information, stores some information about what we observe. And so one sweep actually reads of both memory and also gives us some information about dynamics of the system. Okay. Fine. So why this is quantum? Okay. So the quantum part is that actually this hysteresis is basis dependent. So depending on the basis that we change or we choose to modulate or influenced by our programmable device, you will see different shapes of hysteresis. So once you have a loop, for example, at the output, if you modulate Z basis, X basis, or Y basis on, so these are the directions of the Bloch sphere, you will see that there are different shapes. Okay, so this is one of the signatures. And this basis sensitivity is actually impossible to reach by any classical memory store, and in this original definition sense. So you can wire many memory stores, and you can reach neuromorphic quantum network. So in the sense of the BOF-net sense, but it's still like not purely quantum. This is what I started working at this model. So once I understood how this works, I started to think, okay, so but it's not like fully quantum. We perform measurements, so you can simulate this very efficiently. And the other thing is that actually, because like this update rule that you can somehow manipulate, you can have this built-in fading memory if you have the system. And let's say if you have n qubits, you have extremely large dimensional space. So so you already know that the geometry of high dimensional space is not the goal itself, but essentially it can be useful for some purposes. Okay, so this measurement back action gives nonlinearity for free. Okay, and this is the usual approach. This is the obvious thing. This is what everybody is working on. And the current state of art is that actually, if you perform this kind of simulation using a few memory stores, like a bit something like quantum memory stores, you will run some benchmark. So this is one of the standard benchmarks for signal processing. So for time series, there's this number 10. So quantum reservoir will actually is given by this red signal, and the target signal that it has to learn to copy is this blue blue signal. Okay, and what happens is that basically, if you compare this to a similarly modest classical counterpart, it will perform, let's say, not so bad, and actually, but there will be no quantum advantage. Okay. So, but it's actually noted by authors of this research. This is research from 2 years ago, that if you actually have to keep this dynamics at the edge of chaos for it to perform at its best. Okay, so edge of chaos. This means that your dynamics becomes unstable to some extent. Okay. Yes, so now we go to this essential part, so quantum machine learning part. So you perhaps are familiar with this ideas of Hopfield, and you can store patterns as energy minima if you have this. Okay, this is energy function. This is uncoupling parameters. These are spin variables, so there's the spin up, spin down configurations. So you can store patterns in parameters of psi here. Okay, Basically, this is something that is used for pattern encoding and retrieval and for filtering and so on. So we can try to build a quantum version. This is not the original idea, but it has been done before. But usually what you do, you apply some transverse field here and you replace this classical labels with operators, spin operators. And you can say that's still the same. You encode patterns in coupling parameters, classical parameters, and omegas, this transverse field, okay? So, but now the advantage is that actually you can drive like quantum annealing that we know already that can help with finding global minima. But anyway, if we use memory stores, okay, so what happens? It actually means that effectively this capital J matrix actually builds itself, so no training algorithm, okay, depending on the parameters that we actually want to reach. And this basically means that we can have some, let's say, simulation that each qubit gets its own memory store, and we stream photon encoded patterns. Okay, so so we can actually plot how these parameters ij are learned, and also so have this see that it's actually feasible to encode them. And we can also see how this theory curve, okay, so depending on the age of the pattern here in the gamma parameter is, let's say, matched by our simulation. So, well, it's not perfect, but it's a very crude simulation. So I didn't. So this is not publication level simulation. This is for this presentation, but it's not bad. So we can. So basically, this is just to show that we can do this in principle. Okay. So what is the trick to go to fully quantum regime? So the fully quantum regime requires building something that we have on the right side of this in this slide. So there's a device, and you can think that there is synchronized photon train. Okay, so the photon enters this target part of 3 qubit gate. Okay, so physically we can build a unitary transformation that if there are no photons in a specific required state in a program mode and control mode, nothing happens. Okay, so it's not required that we have all 3 qubits physically present. So a qubit is the polarization state of the photon. So photon goes through, it's looped in a way that it goes to a program mode. If there is, okay, just target and program, nothing happens, okay, because there is no control in here. So so at the same time, the next photon in the train is delivered to the target. And then this first photon that we analyzed leaves this program mode and enters the control mode. And then it's looped, and then it leaves this device. But at the same time, the third photon enters, and when the 3 meet, they actually implement this unitary 3-qubit gate. Okay, it is the same as to say that, okay, I have like a 3 copies of this qubit and I run them simultaneously, and then I just have a look at this one output. But the problem is then, okay, what to do with those extra copies? Do I have to follow them or not? Well, I don't need them at all. This is the point, okay? So that's why it's better to have it in this sort of way. So this is like a, let's say, shot-dependent device. And if we have a look at optical implementations, so shots are cheap. Okay, so this is a motivation for doing this, but the synchronization is the really hard part here. Okay, so, and the thing is that now we have coherent loops, no measurement. This measurement is just to follow what happens to this input stream of photons at the output of this looped nonlinear dynamics. Okay, and this is the dynamics is actually unitary. But because there is, we start with like 3 copies of the same state, this is a built-in nonlinearity, okay? So this provides you the nonlinearity, the multi-copy approach. And then you start with this, and you just build on this by looping through the system. And the loops themselves, they work as a sort of a memory, but you don't need like a huge memory, so you don't have to store these qubits forever. You just need to store them for 2 cycles, okay? So that's not that bad. And what happens next? So this memory becomes, let's say, in superposition. So you cannot now think about a single hysteresis because it will be very strange. In principle, it could happen that it could store this memory a superposition of patterns, okay? So they could be like multiple shapes of patterns in superposition at the same time. Okay, but if you have 2 memory stores like that, you can analyze their outputs, correlate them, and you will see that they could violate Bayes inequality, so they could be entangled. So it just shows that it's still interoperation because like you cannot, using random qubits, correlated classic qubits violated this. Okay, and just to maybe show you how to think about this in a way that's actually useful, I prepared this animation, and this is basically the red arrow is the one that describes you the effective, let's say, state if you perform measurements, okay? Because what happens is that you can think about quantum trajectories. So it means, okay, maybe a photon is in superposition, but perhaps in this 3-qubit gate, one of the, let's say, one possibility is one of the possibilities was that it actually collapsed at being in one of the modes, program targeted control modes, and then the decision was made what happens next. Okay, so when this decision is actually made in what was position that one of the photon is collapsing, then it could go to another port and then collapse to another position. Okay, so if it was like this, that it actually just keeps being coherent just between entering modes, then you have multiple trajectories, and you can use let's say Monte Carlo methods to just to plot this red arrow. Okay, and it is so that well, this is precisely why we use quantum computers to avoid this, because we soon have exponentially many possibilities that we don't want to track them. Okay, and in the end, we just are interested in the outcome of all those superpositions. So so I can write an equation that will like use some sort of a memory kernel and other let's say advanced mathematics to show you what's happening here, but I don't think there is no point of doing that, because this picture actually shows you this. Okay, so you have evolution that's basically a combination of rotations and let's say contractions and extensions of this vector, and actually you would like to have it to have constant length for it to be let's say unitary, unless you want to introduce noise somehow. Okay, so the noise should be like is here. I think about this as noise dependent, so basis dependent. So it means that just the projection on some specific basis is truncated. Okay, and there's also this thing that if you have if you have like specific line at which you just have some attenuation, real attenuation in your system. So for example, 0 collapses to 1, like relaxation in real quantum computers. You could even see some, let's say, randomization. So there is like random superposition of 0 and 1, and then it recovers its quantum coherence just by being relaxed to this ground state. Okay, But if you just forget about this and you modulate the input, okay, that was for not, so this was for not modulated input. So this was just for a state that is just enters this loop. Each copy is the same. I don't modulate the input. This is what I have, that the output. So it stabilizes. This is Trace dynamics, and this is with modulated input. So this is the only difference. Okay. This is what happens step by step by just the input is being modulated. So we start with we just go through this continuous trajectory from top to bottom, okay? And there are some state collapses that drive it. If you use just weak values for weak measurements to interpret these points. Okay, but this is perhaps very intuitive, but this is not the point of why we do this. The point is that what we hope to observe is that if I start with ideal, let's say, state, and I stabilize this pattern that I want to have, and what happens if I insert then this perturbed state, okay? So if I use an optical element like a half-wave plate, this means that actually this, if there will be some delta rotated, the original state would land here, and this perturbed state would land here. So this is no correction, just for single device, okay? But since this in this fully quantum coherent regime, this actually will interact also with two of its predecessors, and will also be then interacting with some successors in the train. So if there is like just a random let's say disturbance, it will actually recover. Okay, but so you can see here that if you have so there's this recall overlap. So if you have a look at this let's say framework of Hopfield, you will see that if you set this capital omega to 0, you have classical regime, and if it's larger than 0, you have quantum regime. Okay, and if you just look at this trained network parameter, so if you just have this percent of bit flipped at random, perhaps this is this perturbation. You can see that it could be translated in this way, that it's just the amount of flipped blue arrows. If it's low enough, it's below like 30%, the recovery, if you have this quantum part activated, it's better. Okay, so this is the plot that I generated using about like 10 trajectories, so it's not that significant, but the trend persists if you increase the number of simulations, and then it's let's say visibly worse after like in this large area regime. So classical memory stores behave better if there is a lot of noise, but if the noise is low, you can see that there is some possible quantum advantage here, okay, for pattern recovery. Okay, so one thing that you could do, you can also use like two quantum memory stores I already mentioned. You can put them like together next to each other, and put a controlled phase gate between the outputs of these two. So you could drive one memory store with one frequency, the other one with another, and you could then see that there is some this transient dynamics here implemented, and finally it stabilizes at some pattern. So again, there is another thing that you could let's say think about as some pattern encoded in time, because it's this concurrence that tells you how entangled these two outputs are. Okay, so this is in perfect case, no errors whatsoever. So this gamma, just this forgetting rate of stabilization is related to the way that we construct our update rule or how we interpret, let's say, the program. So this is what we have to set at hardware level, but this is like a knob that we can classically set. Okay. And this, so this is created by this controlled phase gate with maximum phase. So this is CZ, let's say, gate. And it easily can beat this classical, let's say, limit for Bell inequality violation. So classically, we start at 2 if we have, let's say, photons in the same input state. And then it's this, if we just scan the phase of this gate from 0, so nothing happens, to pi, that means that we introduce, if both photons have are in the state of level 1, we have phase -1 phase difference. Okay, so this is what we will see, perfect increase in this Bell parameter. Okay, so this is quite complicated. So there are many methods that are mainly not suitable for this like format to discuss. But the take-home messages are, I think, rather simple. So even if you have like a photon and a half-wave plate plus feedback, you can build a programmable quantum memory store, at least at single photon level. And this memory of such a memory store, you can think about this like a tunable non-Markovian kernel. Okay, so there is this hysteresis loop, and its area is like spectral density of what's happening at the output. Okay, and if you have this basis dependent hysteresis, you can introduce some parameter that tells you, okay, how quantum is this hysteresis. But this parameter is not like ultimate quantifier of quantumness for this. This is just for convenience. But the real thing happens if you think about like this fully coherent 3-mode quantum gate, and if you network both of them like this simple idea that was studied, and it's being studied experimentally now for like 2 years. You can see that this networked reservoir computing and associative memory with this Hebbian learning is actually implemented just by physics of the system. You don't have to do this algorithmically. You just have to set the right parameters and use the right circuit architecture. So finally, if you use this coherent loop delayed upgrade, this will make the memory entangling, and you can certify it. Okay, so this is like Bell certifiable. So this means that well, it cannot be explained by classical theories. So, and usually, if it cannot be explained by classical theories, it cannot be efficiently simulated. So we expect that there could be some quantum advantage here. So the real lesson is that quantum systems can remember coherently, and that's the surprising part, because if you don't use this framework that I just discussed, and I think, well, I don't know any prior works on this that use it this way and introduce it this way, you discover that, okay, everything is coherent for all the time, and you recover at the same moment many characteristics of reservoir computing. Okay, so the only collapse that happens is actually at this measurement point. So where I would expect some classical effects is when I measure. So after entangling 2 memory stores, I have to perform some measurements like concurrence measurement, Bell inequality certification, something like that. So this is where the like intentional decoherence happens. And when we observe how these outcomes are modulated, they just happen to have the characteristics of something that is described by by this dissipative stochastic differential equation. Okay, so that's the point. but there is no real dissipation. It's just modeling it by having feedback loops. Okay, and there is like a rather rich literature on this. So this is so concepts are already 10 years ago, and first experiments were also performed like already 4 years ago. And this is related to other ideas that probably you are very familiar with, but we actually built something like this free mode coherent gate that is programmable phase gate in 2013 an optical table. Something that's even more similar, quantum rotor. So we have, and this work is actually, we have a manuscript ready, but I'm fine-tuning it. Is done by us over the course of the last few years once we learned about this approach to memory stores, and we just ask ourselves, okay, what would quantum version of classical memory store work like? Because we already have quantum versions of inductors, of capacitors, of resistors, but the genuinely quantum memory store, I think, is something that nobody has discussed before. I mean, honestly, by tracing its coherence for the whole operation life cycle. Okay, thank you for your attention. So now I'm open to questions, and so if you have any, just please go ahead and ask, or I can also see the chat. I see that there is one question. Okay, I will just close sharing screen.
Okay, thanks. Thank you, Karol. So actually, the previous questions were addressed to Jacob. So I see that Jacob has already answered. Okay, but maybe someone would like to ask a question to Karol, or maybe someone would like to answer it. I don't see questions now. Let's maybe wait for a while, and if anyone has any questions, because this was the last talk, you can just unmute. You do not have to type it on the chat.
Okay, I'm ready to answer. But I see that there's only one comment about autocorrect. So basically, this is like autocorrect for quantum, for photons. Okay, so.
Oh, all right. Okay.
I have a question.
Please.
What does non-Markovian like kind of mean in this context?
I see. Okay, so non-Markovian, this means that the evolution depends on the previous step. Okay, and if you include memory, this is essentially violates this assumption of Markovianity. So this means that if you have something that resembles a random system and it evolves from one point seemingly randomly to another point, it actually, the decision that it makes between the steps are influenced by the past steps. Okay, it's only like one step to another step. You have to take a look back. So if it remembers more than one step before, this means that it's not Markovian. So this is how we call it in physics. Also in mathematics, in process theory. So.
Okay,
Thank
good.
you.
So in the meanwhile, I can see that Kartik asked a question to Jacob. So Jacob, if you are still with us, you can
so I'll
try to answer. Okay.
Sorry, just pick it up. How much of quantum natural gradient can be improved with Feynman path integral? I don't know. I would have to think about it. I know that quantum natural gradient as a optimization technique, it's only very recent, and there's a lot of scope for further improvement. It could be that the path integrals could play some role in it, but it's a hard question to answer right now. Yeah.
Okay, good. And I see that Nicholas would like to ask another question. So Nicholas, you can also unmute.
Hello. How would you kind of like describe like error correction, like in like your geometry and like in terms of your slides?
It's a question for me? No.
Yeah.
To
Was for
Jacob.
Michał.
To Jacob. I think this was to Jacob, right? Or
Yeah, to Jacob.
Okay.
Mhm.
Well, look, it's actually error correction. It's a very important process because when you have especially classical optimizer, it follows the classical landscape. The point selected on the landscape may not necessarily map onto your pure state, and so there is actually constant error correction which must take place in this process. Otherwise, your computation may have real difficulties. It may be a decoherence happening. So yes, it's actually error correction must take place, especially when you have classical optimization happening. And also, what you need to remember is that the mixed states on the surface of a high-dimensional manifold, they're exponentially more mixed states on the surface than pure states. And so there is this constant pressure to get it's a geometrical force basically, which is trying to move you away from pure state path towards the optimum. So I don't know if we're going to overcome that because it's nothing to do with hardware. It's to do with the geometry.
Mhm. Okay, thanks.
Thank you.
Nicholas, I hope that it answers your question. Okay, there's another question from Isaac. I'm not sure to whom, but I will read it and we'll see. How much of the exponential speedup in algorithms like quantum SVM or HHL actually survives once you account for the cost of loading data into quantum memory? I think it's mainly to Carl, I guess. Not sure if you can answer.
Okay. So my answer is that I haven't checked for that yet, but because like this is the different let's say application focused approach. Okay, so so this paradigm to reservoir quantum computing is let's say such that you just set parameters and you just wanted to wave to a way of let's say to remember some patterns. But there's an interesting connection to this question. I mean, if you don't want to implement quantum correction codes, perhaps you can rely on some auto let's say self-correcting, okay, autonomous error correction code. So this is something that I've been working on, and if it's let's say if it works, then you don't have to worry about syndromes. You don't have to do this whole standard let's say classical, because it's taken from classical computing, error correction pipeline. You just modulate the dynamics in such a way that and you use your logical words in such a way that they are like patterns, quantum patterns that just rectify themselves by passing through network. So this is the goal here. So this is what we want to achieve. Okay, and once we do that, we have like let's say this memory protected logical qubits. We could maybe spend less or even entirely remove this necessity of error correction. Okay, so this is what I think is important here.
Okay, good. Thank you. Thanks, Carol. Do we have more questions to any of the remaining speakers? I'm just checking the list of participants. Yes, it seems that Arthur is no longer with us, and I do not see Sven, but the other speakers are here. Okay, the last chance. All right, if there are no more questions, then I would like to thank once again all the speakers for the great presentations and of course all the participants for coming, for attending this event. It's already the 6th edition of our conference, so I'm very happy that we are able to continue it, and we'll do our best to organize it next year as well. I hope you enjoyed, and we'll try to upload the video recording to our YouTube channel. So I will send you some emails later. Thanks, and now I will stop recording.